Hello there and welcome to Just About Earth, where we take difficult questions, lower the volume and look at them carefully enough that even a block of granite can have its say. Tonight, we are going to ancient Egypt, but not to begin with a pharaoh, a tomb, or a line of workers pulling a stone on a wooden sledge. We're beginning with a damaged block lying at Abu Rawash, a pyramid site northwest of Giza, and with a set of marks that some observers believe should not be there. The block is not decorated. It does not carry a royal face, a prayer, or a neatly carved name. At first glance, it looks like one more broken piece among the remains of a heavily ruined monument. Yet its surface has drawn unusual attention because it appears to combine several different features. There are fine parallel lines. There is a broad concave form rather than a simple flat cut. There are curved boundaries where one worked surface meets another. There are changes in level that can be interpreted as separate passes of a tool. Put together, these details have led some researchers outside conventional Egyptology to propose a remarkable possibility, that the stone was shaped by a large machine using a controlled multi-stage cutting process. That is the claim we will examine. We will not assume it is true simply because the marks look impressive, and we will not dismiss it simply because the proposed machine sounds unfamiliar. Ancient stonework attracts both overconfidence and eye-rolling in roughly equal amounts, which is not always the ideal atmosphere for a careful investigation. A groove in granite can become proof of a vanished civilization before breakfast, while an awkward explanation involving sand and patience can be treated as settled before the kettle is boiled. Our task is to slow down, define what is actually visible, ask what different tools would leave behind, and keep separate the evidence, the interpretation, and the much larger story built around it. Before we go farther, where are you listening from tonight? Are you somewhere close to old stone buildings, or in a place where nearly everything around you is made by modern machines? When you see a surface that looks precise, what is your first instinct? Do you imagine skilled hands, a clever guide, a simple tool used for a very long time, or a machine whose moving parts have disappeared? If you enjoy these calm investigations into old mysteries, you can like the video and subscribe to the channel. It helps more curious people find this quiet corner, especially those who prefer their ancient mysteries with a little less shouting and rather fewer red circles drawn around blurry photographs. Now settle in, get comfortable, and let us begin with the most important point. No machine has been excavated at Abu Rawash that can be identified as a giant stone-cutting saw. There is no 11-metre bronze disc resting beneath the sand. There is no surviving axle, bearing, frame, drive system, or workshop wall showing how such a device might have been mounted. Even advocates of ancient power tool theories acknowledge that the proposed equipment has not been found. The machine is reconstructed from the stone marks themselves. Supporters of the idea look at the curvature of the cut, extend that curve into an imagined circle, and estimate the scale of the tool that could have produced it. One influential reconstruction describes a circular saw approximately 37 feet, or just over 11 meters, in diameter. Depending on exactly which line is measured, how the block is oriented, and whether the surface is interpreted as the path of a blade, or the movement of the workpiece, the reconstruction can become very large indeed. This kind of reasoning is not automatically foolish. Archaeologists and engineers regularly infer missing tools from the traces they leave. A drill hole can reveal the diameter of a drill. Repeated parallel grooves can suggest a direction of motion. A kerf can preserve the width of a cutting element. Curved scoring can indicate rotation. Modern investigators can often distinguish between surfaces that were sawn, ground, drilled, struck, chiseled, or polished, even when the tool itself has vanished. Crime laboratories do something similar with tool marks, although the average granite block is generally less cooperative during questioning. The difficulty is that stone does not preserve a complete video of how it was worked. It preserves a final surface that may have been cut, corrected, weathered, broken, reused, buried, exposed and handled by people across thousands of years. One mark may record the main shaping stage, another may come from later dressing. A curved edge may be the end of a controlled cut. or it may be part of the natural fracture that exposed the cut. Parallel lines may record steady mechanical movement, but they may also form through abrasive particles dragged repeatedly along similar paths. A precise interpretation therefore requires measurements, close imaging, geological analysis, practical experiments, and preferably several comparable examples. A photograph can begin the discussion, but it cannot finish it. Abu Rawash is a useful place for such an investigation because it is both historically important and badly disturbed. The site lies about 8 kilometers northwest of the Giza plateau and contains remains from several periods. The pyramid complex on the high ground is attributed to Djedefre, a son and successor of Khufu, largely because excavations found inscribed fragments of royal statues connected with him. The wider area also contains much earlier First Dynasty burials as well as later remains, showing that this landscape was used over a long span of Egyptian history. That history matters because finding an old object at the site does not by itself tell us exactly when every exposed surface was cut or altered. Djedefre's monument has suffered extensive destruction and stone removal. What survives today is not a sealed workshop frozen at the moment construction stopped. It is a ruin that became a source of building material, with blocks broken, shifted and carried away. The missing pyramid has encouraged dramatic stories, including old suggestions of deliberate destruction after a royal family conflict, though archaeological accounts place much of the heavy quarrying in far later periods. This does not make the surviving tool marks meaningless. It does mean that their context has to be handled carefully. A block lying near a pyramid may belong to the original building program, but its present position and condition may not preserve the exact sequence of ancient work. The conventional explanation for cutting hard Egyptian stone is not that soft copper sliced granite in the way a steel knife slices fruit. Copper tools could act as holders, guides, or carriers for harder abrasive grains. Quartz-rich sand placed beneath a copper saw or around a tubular drill could do much of the actual grinding. Experimental archaeologist Dennis Stocks tested reconstructed copper saws and drills on Aswan granite and demonstrated that abrasive methods can remove hard stone, although slowly and with considerable wear to the tool. In one reported test, a copper saw used with sand cut a groove into granite over many hours. The copper did not need to be harder than every mineral in the rock because it was helping to press and move abrasive grains through the cutting area. The experiments do not prove that every ancient mark was made in exactly this way. They do, however, show that the statement copper is softer than granite is not enough by itself to rule out copper and abrasive technology. This is where the Abu Rawash debate becomes more interesting than a simple argument between primitive tools and advanced machines. The real question is not whether sand can wear granite. It can. The harder question is whether the proposed method can reproduce the specific geometry, regularity, and sequence seen on this block. Can a hand-operated saw with loose abrasive create long, evenly spaced striations? Can it form a smooth concavity in more than one direction? Can it leave a sharply bounded, curved termination? Can multiple passes explain the steps without requiring the blade or the stone to wander? Can the changes in the surface be reproduced consistently rather than explained after the fact? Should the answer be yes, the known toolkit remains a strong explanation. Should the answer be no, we must ask what additional controls, frames, guides, motions, or machines were used. The word machine can be misleading here. It often makes people imagine electricity, steel bearings, digital controls, and a worker in safety goggles checking a control panel. But a machine is simply a device that transmits or modifies force and motion. A bow drill is a machine. A lever is a machine. A weighted saw held in a frame is a machine. A rotating platform, a pendulum arrangement, or a guided cutting rig would also qualify. Ancient societies could use machines without possessing modern industry. The Egyptians clearly understood ropes, sledges, levers, boats, ramps, drills, careful measurement and organised labour. The question is not whether ancient Egypt used mechanical devices, it certainly did. The question is whether its craftspeople possessed a category of large, precise stoneworking equipment that has not survived and has not yet been convincingly reconstructed from the known evidence. Supporters of the advanced machining interpretation believe the block answers yes. They point to what they describe as feed lines, repeated striations that appear to cross the different mineral components of the granite without noticeably changing direction. They argue that the main surface is not merely curved in one simple direction, but concave in a more complex way. They identify arcs and steps that appear to record separate cutting stages. From these features, they propose that a large circular blade passed through or across the stone, while either the blade, the block, or both were repositioned between operations. The largest reconstruction is based on extending one observed curve until it becomes a complete circle, producing the proposed diameter of roughly 11 meters. That proposal immediately creates practical questions. What was the blade made from? How was a disc of that size kept rigid? Was it truly a complete disc, or could a shorter, curved cutting arm produce a similar arc? What powered it? How was the granite secured? How was abrasive delivered into the cut? How fast did the cutting surface move? Where are the remains of the support structure? Could wood, rope, copper, stone bearings, and human or animal power produce enough stability? Most importantly, what trace would such a machine leave that a framed hand saw, a pendulum saw, a grinding tool, or later weathering could not? A proposed diameter also sounds more certain than it may be. When only a short arc survives, more than one larger circle may fit it if the original orientation and complete geometry are uncertain. A small error in the measured curvature can produce a large change in the reconstructed radius. If the cut lies on a surface that is itself curved, tilted, or broken, a photograph can make the apparent arc look tighter or flatter depending on the camera angle. This is why proper three-dimensional scanning would be valuable. It could map the surface, separate real geometry from perspective, measure the spacing and depth of the lines, and test whether the different features share a common centre of rotation. Photographs remain useful, but photographs can encourage the mind to complete patterns. We are good at seeing circles from fragments, faces in stone, and straight lines where erosion has removed the untidy portions. That does not mean the Abu Rawash features are imaginary. It means a serious case must be built on measured surfaces rather than visual confidence alone. The most convincing investigation would publish detailed scan data, identify the granite's mineral structure, record microscopic wear patterns, compare protected and weathered regions, and invite competing teams to reproduce the marks. The result should not depend on whether the viewer already wants the object to be mysterious. The same standard should apply to the conventional explanation. It is not enough to say copper and sand worked in an experiment, therefore copper and sand made this surface. Experimental cutting has established possibility, not automatic identity. A reconstructed tool should be tested against the exact features under discussion. When an ancient surface contains regular lines at a measurable spacing, the replica should be examined for the same pattern. When the block has compound curvature, the experiment should explain the toolpath that creates it. When a cut ends in a clean arc, the process should show how that termination forms. Archaeology is strongest when it moves from a general method to a specific match. This approach can feel less exciting than declaring a lost high-technology civilization, but it leads to better questions. Suppose, for example, that the marks do require a guided apparatus. That would not immediately prove the existence of a forgotten builder culture predating the pharaohs. It could instead reveal an ingenious Old Kingdom workshop method, using mostly perishable materials. Large wooden frames, ropes, leather fittings, copper elements, and abrasive systems might leave very little behind, especially at a site later quarried. A technique can be sophisticated without being industrial in the modern sense, and lost knowledge does not always require a lost civilization. Sometimes it requires only a specialized craft tradition that was never described clearly and later stopped being used. A a forgotten machine does not have to be a mysterious machine. Think of an elaborate wooden loom, a shipbuilding frame, or a lifting rig. Without written instructions or surviving examples, later people might struggle to reconstruct it, even though every component was made from ordinary materials. Wood decays, rope breaks down, leather disappears, copper is recycled, stone survives, so the stone may preserve the clearest remaining trace of a device that was mostly made from things that did not survive. On the other hand, the broader alternative theory goes much farther. It proposes that Egypt's earliest monumental sites were inherited from an older builder culture with advanced engineering abilities. In this view, dynastic rulers did not necessarily create every major stone structure from the beginning. They may have repaired, modified, decorated, enlarged, or claimed monuments that were already ancient. Djedefre's connection to Abu Rawash would then show royal use of the site, but not necessarily the first shaping of every granite block found there. A royal name on a statue could identify the ruler who occupied or developed the complex without identifying the original makers of every object within it. This is a substantial claim, and it needs substantial evidence. Archaeologists know that Egyptian kings reused older objects and building materials, restored temples, erased names, inserted their own inscriptions, and altered existing monuments. Reuse was part of Egyptian history. But moving from ordinary reuse to a technologically advanced pre-dynastic builder culture requires more than an unusual cut. It would require a consistent body of securely dated evidence: tools, workshops, waste material, unfinished pieces, settlement remains, distinctive manufacturing traces, or monuments whose construction can be shown to predate their accepted archaeological context. One puzzling block may justify investigation. It cannot carry an entire civilization by itself. At Abu Rawash, the presence of First Dynasty tombs demonstrates activity in the area centuries before Djedefre. But those tombs are not evidence of an 11-metre stone saw. They show that the site had an earlier history, which is important, though far less dramatic. This distinction prevents one true statement from quietly supporting another statement that has not yet been demonstrated. People were here earlier, and those people used advanced granite machinery are separate claims. The first is archaeological fact. The second remains a hypothesis requiring direct support. There is also a dating problem built into worked stone. Granite itself may be extremely old geologically, but that tells us nothing about when it was shaped. The cut surface contains no convenient label saying Tuesday, 4th year of the reign, just after lunch. Dating usually comes from context: where the object was found, what structure it belongs to, associated inscriptions, construction layers, pottery, mortar, quarry marks, and the sequence in which features were added. When context has been disturbed, assigning a date to a particular tool mark becomes more difficult. Even when a block clearly belongs to a pyramid complex, investigators must consider more than one episode. The stone could have been quarried and shaped for the original monument. It could have been corrected during construction. It could have been cut again when the monument was dismantled. It could have been prepared for reuse and then abandoned. A later quarry worker might leave marks on a much older surface, creating a block that records more than one period of activity. This is one reason the debate repeatedly turns to comparisons. Similar marks have been identified by alternative researchers on stone at Giza, Abu Rawash, Karnak, and other Egyptian sites. They argue that recurring kerfs, striations, drill marks, and curved cuts represent a shared machining tradition rather than isolated accidents. If comparable marks appear on securely placed stones from different sites, investigators can ask whether they represent the same technique. Similar features across several locations might suggest a long-lived method. Differences might reveal that several unrelated processes have been grouped together too quickly. A line that resembles a saw mark from a distance may prove under magnification to be a grinding scratch, a dressing mark, a fracture feature, or a later cut. The comparison must therefore be more exact than placing two photographs side by side and noticing that both contain lines. Researchers would need to compare the width of the kerfs, the spacing of the striations, their depth, their direction, the mineral grains they cross, the shape of their endings, and their relationship to surrounding surfaces. Two blocks may both appear machined, while preserving completely different kinds of work. There is something valuable in the attention given to this uncelebrated piece of granite. Famous monuments often encourage us to look at overall size and forget manufacturing detail. We admire the pyramid but overlook the corner where a cut ran too far. We photograph the polished wall, but ignore the abandoned piece that may preserve a tool's path more clearly. Finished surfaces can hide the process. Mistakes, incomplete cuts, and discarded stones may tell us more because they preserve moments when the work stopped before the evidence was polished away. A perfectly finished granite wall tells us that the craftsperson succeeded. An overcut tells us how the tool was moving when something went wrong. A partly drilled hole can preserve the diameter and motion of the drill. An abandoned groove may show whether the cutting element was straight, tubular, or curved. For anyone trying to reconstruct a lost technique, imperfections can be more useful than masterpieces. That is what makes the Abu Rawash block worth examining, even if the largest claims eventually fail. It asks us to think like investigators rather than tourists. What direction did the tool move? Which marks came first? Where did pressure increase? Did the worker change the angle? Is the curve intentional? Does the surface reflect rotation, rocking, grinding, or repeated straight strokes? Could a large blade remain stable enough to create it? Could a smaller tool create the same geometry by moving the stone beneath it? What would the waste material look like? How many people would be needed? How long would the operation take? Would the machine save labour? Or would maintaining it require more effort than a simpler method? None of these questions requires us to underestimate ancient craftspeople. In fact, assuming they could only strike stones together is its own form of carelessness. Egyptian builders organised quarrying, transport, measurement, levelling, masonry, sculpture, and finishing on a huge scale. They did not need modern motors to be intelligent, and they did not need mysterious technology to be impressive. Respect, however, should not become an excuse to stop investigating. Saying ancient people were clever is not a technical explanation. We still need to know what they built, how it moved, what touched the stone, and why the marks look the way they do. The opposite mistake is to assume that anything difficult must come from an unknown culture. Modern people often underestimate what patient work can achieve. A process that removes only a small amount of granite each hour may sound hopeless until we imagine teams working for months, tools operating simultaneously, and experienced craftspeople who spent their lives improving one specialized task. Slow does not mean impossible. Simple does not mean uncontrolled. A wooden frame can hold a tool at a consistent angle. Ropes can maintain pressure. Counterweights can reduce effort. Repeated measurement can produce accurate results. Abrasive grains can cut material much harder than the metal carrying them, yet patients cannot explain every pattern automatically. When a surface shows a feature that an experimental process does not reproduce, saying the workers simply spent longer does not solve the problem. More time with the wrong motion still creates the wrong mark. The geometry matters as much as the cutting rate. So tonight we are not choosing between genius and mystery. Ancient skill is certain. The exact method is not. The block may preserve evidence of a known abrasive process used with greater control than experiments have so far demonstrated. It may record a lost but historically plausible mechanical rig made mostly from perishable materials. It may have been misunderstood because photographs exaggerate its geometry. Or it may point toward a method that does not fit comfortably within current reconstructions. Each possibility can be tested, but only if we resist turning uncertainty into proof. The advanced machine theory must explain where the power came from, how the tool was built, and why its physical components have not been identified. The conventional theory must reproduce the unusual marks rather than merely demonstrate that granite can be worn away. The older builder theory must provide evidence of a culture, not only evidence of workmanship that looks surprising. These are demanding standards, but they protect the mystery from becoming a story that can never be questioned. A useful theory risks being wrong. It makes predictions. It tells us what measurements to take, what traces to look for, and what an experiment should produce. The first step is to look closely at the place where the object was found, because Abu Rawash is not merely a name attached to an intriguing photograph. It is a complex archaeological landscape, occupied during different periods, connected to one of the most powerful royal families of the Old Kingdom, stripped for stone, excavated in stages, and still capable of confusing anyone who expects a ruin to keep its history neatly arranged. To understand why this particular block has become central to the argument, we need to examine its setting, its shape, its damaged edges, and the precise marks that have been interpreted as the work of a machine. The precise marks that have been interpreted as the work of a machine cannot be understood without first looking at Abu Rawash itself. The block did not come from a clean laboratory excavation, and it was not discovered in a sealed room with its original tools resting beside it. It sits within one of Egypt's most damaged pyramid sites, a place where ancient construction, later destruction, stone quarrying, excavation, and modern attention have all left their own traces. Abu Rawash, sometimes written Abu Rosh, lies northwest of Giza on elevated ground overlooking the edge of the Nile Valley. From parts of the site, the pyramids of Giza can be seen in the distance. The location is close enough to belong to the wider pyramid landscape around ancient Memphis, but separate enough to feel removed from the familiar arrangement of Khufu, Khafra, and Menkaure. The most prominent monument there is associated with Djedefre, a son and successor of Khufu. Djedefre ruled during Egypt's 4th dynasty, the period in which some of the country's largest royal monuments were constructed. His pyramid complex carried an ancient name that can be translated as Djedefre's starry sky, or the firmament of Djedefre, depending on how the Egyptian wording is rendered. Excavators attributed the complex to him after finding fragments of quartzite statues, including pieces bearing inscriptions connected with the king. That attribution is important because it gives us a historical setting for the monument. It does not, however, provide an automatic date for every loose stone currently visible at the site. Abu Rawash contains remains from more than one period. Archaeological work has documented early cemeteries dating to the 1st dynasty, long before Djedefre, as well as Old Kingdom monuments and evidence of later activity. The ground does not preserve one tidy event, it preserves repeated use over centuries. The existence of early burials at Abu Rawash is sometimes brought into arguments about an older builder culture. Since people were using the area before the 4th dynasty, some suggest that Djedefre may have inherited an already important place. That possibility, stated in a limited way, is quite reasonable. Ancient rulers often selected locations that already carried religious, political, or ancestral meaning. The difficulty begins when the presence of earlier people is treated as proof that an earlier technological civilization built the pyramid or shaped its granite. An early cemetery shows that the landscape was occupied. It does not tell us what machines those people used, whether they built monumental stone structures, or whether they produced the curved block now at the centre of this discussion. Keeping those claims separate may seem cautious, but it prevents the argument from running ahead of the evidence. A person can accept that Abu Rawash had a history before Djedefre, without accepting that it contained a lost industrial culture. In the same way, a person can question the standard explanation for a tool mark without rejecting the entire archaeological chronology of ancient Egypt. Djedefre's choice of location has encouraged speculation for a long time. Older accounts sometimes presented him as a rival who abandoned Giza after a family conflict, perhaps following a violent struggle over the throne. More recent archaeological interpretations have been less willing to build a dramatic family story from limited evidence. The decision to build at Abu Rawash may have involved topography, visibility, religious connections, access routes, royal preference, or several factors at once, the high ground offered a commanding position. It also presented practical difficulties. Building there required moving workers, supplies, tools and stone across a landscape that was less convenient than the flatter parts of the Giza plateau. Local limestone could be obtained nearby, but harder decorative stones had to travel farther. Granite would normally have come from the Aswan region in southern Egypt, transported over a great distance before being moved uphill to the building area. That journey alone makes any surviving piece of granite worth examining. Granite was expensive in terms of labour. It was quarried far from Abu Rawash, transported north, unloaded, moved across land, and shaped for a specific architectural purpose. A worker would not casually discard a large granite block in the same way someone might throw away a chipped brick. The block under discussion is commonly described as red or pink granite. Granite is made from interlocking mineral crystals, usually including quartz, feldspar and mica. Its exact composition varies, but it is generally hard, heavy and resistant to wear. The quartz content is especially relevant because quartz can act as an abrasive against other minerals in the stone. Granite is difficult to work, though not immune to repeated grinding, pounding, drilling and sawing. Egyptian craftspeople used granite for statues, columns, architectural fittings, sarcophagi, portcullis stones, and other objects, where strength, appearance, or symbolic value justified the effort. Their ability to shape it is not in doubt. The debate concerns the methods used and whether the marks on certain objects require tools beyond those currently supported by the archaeological record. The Abu Rawash piece first attracts attention because its main worked surface is not flat. A straight edge placed across it reveals a visible hollow. The surface curves inward, producing a broad concavity. From another direction, the end of the worked area also appears to follow a curved boundary. This has been described as compound curvature because the geometry seems to involve more than one radius. To someone familiar with modern manufacturing, a controlled concave surface can suggest a rotating cutter. Place a large circular blade against a block and allow the rim to enter the material, and the blade naturally produces a curved bottom. Change the angle of the blade, move the workpiece, or make several overlapping passes, and more complicated surfaces can appear. The presence of a curve, however, does not identify the tool by itself. A curved surface can be made in many ways. It might be ground with a smaller tool moved repeatedly through an arc. It might result from a straight saw that was guided along a changing path. A swinging weight with an abrasive face could remove material from a curved area. Workers might rough out the form with pounding stones and then smooth it with abrasives. Even a series of short, straight operations can create a surface that appears continuously curved after finishing. Modern craftspeople do this routinely when they make rounded forms without using a cutter equal to the full radius of the final object. The machine interpretation, therefore, depends on more than the basic concavity. Its supporters focus on how regular the curve appears, how the smaller features relate to it, and how lines on the surface seem to follow one another. Engineer Christopher Dunn examined and photographed the block and treated it as evidence of a controlled cutting operation. His measurements, taken with straight edges, photographs, chord lengths, and estimates of the depth of the curve, led him to calculate radii of roughly 24 feet in two directions. Dunn then proposed that both curves could be produced by a large circular cutter tilted at an angle. In his reconstruction, a disc about 37.5 feet across, approximately 11.5 meters, could create the observed geometry. Seen from one direction, the tilted disc would present a circular curve. Seen from another, its apparent shape would be elliptical, allowing the same tool to produce different radii on different axes. It is an inventive solution. It translates the surface into a problem of industrial geometry and asks what kind of moving tool could generate it. Dunn also tested the general concept by making a much smaller model, using a modern cutter to reproduce a compound surface. He argued that a change in the angle of the cutter could create a small step similar to one he believed was present on the ancient block. That reconstruction is the source of the frequently repeated claim that ancient Egyptian builders used a circular saw approximately 11 meters in diameter. The number was not found in an inscription, and it was not taken from a surviving blade. It comes from fitting a proposed toolpath to measurements taken from the block. There is an important difference between showing that a tool could make a shape and showing that it did make the shape. A modern cutter can reproduce many ancient forms, but that does not mean the ancient workers used the same device. A computer-controlled milling machine could carve a convincing copy of a Roman statue. The finished resemblance would not prove that Roman sculptors had computer-controlled mills. To identify the actual process, the reproduction must match more than the overall shape. It should create comparable scratches, edge conditions, steps, surface roughness, and errors. It should also fit what is known about materials and workshop practice from the relevant period. The proposed 11-meter saw faces an immediate engineering challenge. A disc that large would be difficult to manufacture and support even if made from modern metal. A thin blade might bend under its own weight. A thicker blade would become extremely heavy. Any irregularity near the outer edge would be magnified as the disc rotated. The central bearing would need to handle substantial loads, and the structure supporting it would have to keep the cutting rim aligned with the stone. Dunn's interpretation treats slight side-to-side wandering in the surface lines as possible evidence of blade wobble. He argues that the striations move together in parallel rather than appearing as unrelated scratches, which in his view suggests fixed cutting points attached to a common moving tool. He estimates the spacing between some lines at approximately 0.03 to 0.06 of an inch, or around 0.75 of a millimetre to 1.5 millimetres. If those measurements are accurate and the lines genuinely form repeated, corresponding paths, they deserve close attention. A rigid tool with projecting teeth might leave such marks. A blade carrying embedded abrasive pieces might also produce them. Yet loose abrasive can create parallel scratches as well, especially when trapped beneath a guided tool and dragged back and forth over the same area. Experimental work with reconstructed Egyptian-style copper saws has shown that granite can be cut using sand as the active abrasive. In Dennis Stock's experiments at Aswan, weighted copper saws created grooves in granite, and the resulting cuts included parallel striations. The process was slow and consumed copper, but it demonstrated that a soft metal tool combined with harder abrasive grains can work a much harder stone. A loose grain caught between a copper blade and granite does not simply roll about without direction. Pressure can embed it temporarily into the softer metal. Once held, it behaves more like a cutting point. It scores the stone until it breaks, becomes dislodged, or is replaced by another grain. Thousands of such events occur during sawing. This means that a scratch resembling the path of a fixed tooth does not necessarily prove that a permanent tooth was mounted in the blade. Temporary abrasive grains can also leave linear marks. Repeated strokes in a guided groove can cause later grains to follow earlier paths, producing a degree of parallel order. The disagreement therefore turns on the exact character of the lines. Are they random scratches that merely run in the same general direction, as expected from abrasive sawing? Are they evenly spaced ridges with corresponding side-to-side movement, suggesting several fixed points moving together? Do they cross quartz crystals in the same way they cross softer minerals? Are they cut into the surface or raised between adjacent grooves? Do they continue without interruption across the full worked area? These questions cannot be answered confidently from ordinary photographs. Lighting changes the appearance of shallow marks. A low sun angle can make tiny ridges look deep. Compression in a digital image can merge several scratches into one line. Dust can fill part of a groove, while moisture can increase contrast elsewhere. A proper study would require close-range photogrammetry or laser scanning, microscopic imaging, measurements at many locations, and mineralogical mapping. Investigators would need to separate the original working marks from weathering, damage, and modern contact. The condition of the block adds further uncertainty. Dunn reported that the object had been raised onto rough supports before he examined it. This may have made the surface easier to see, but it also indicates that the block's modern position was not original. Someone had moved or adjusted it, though exactly when and why may not be clear from the published account. The exposed surface has also spent an unknown amount of time in the open. Windblown sand can abrade stone. Temperature changes can weaken mineral boundaries. Salt growth can cause grains to detach. Visitors may touch, climb on, clean, or reposition objects. None of this is likely to manufacture a complete compound curve, but it can modify the finer lines used to interpret the method. The block's original purpose is another unresolved issue. It is sometimes described as a possible sarcophagus fragment. If that identification is correct, the concave area might belong to a hollowed interior, an unfinished lid, a corner, or a piece broken during manufacture. Other descriptions treat it more generally as an architectural fragment. A sarcophagus connection would be significant because the process of hollowing a granite box differs from cutting a flat paving slab. Workers might use deep saw cuts to define sections, drills to remove internal material, pounding stones to break away ridges and abrasives to smooth the walls. An unfinished or damaged piece could preserve marks from several stages. The sequence matters. Consider a block that was first sawn, then ground, then broken. The saw might leave straight or slightly curved lines. Grinding could soften the surface into a shallow concavity. The later fracture might create an edge that appears related to the curve even though it formed afterward. Reverse the sequence and the interpretation changes. A block might first be given a curved form and then receive repeated finishing passes. Those later scratches would describe the surface without creating its basic geometry. Looking at the final piece, it would be easy to assume one tool produced everything. Dunn's reconstruction proposes a multi-stage cutting process. The cutter would approach the work at one angle, move across part of the surface, then shift position or orientation. A final pass would blend much of the area while leaving a step where the cutting conditions changed. This attempts to explain the main concavity, the curved termination, the step, and the parallel lines through one controlled mechanical operation. The strength of this idea is that it tries to account for several features together rather than explaining each one separately. Its weakness is that each additional stage introduces another assumption. The blade size, tilt, support, material, cutting edge, feed direction, power source, and sequence are reconstructed without a surviving machine or a fully documented workshop. A proposal with many adjustable variables can often be made to fit an unusual surface. The critical test is whether the geometry requires that particular process or merely permits it. One detail often overlooked is that the proposed circle is much larger than the surviving arc. When a short section of a large curve is measured, small differences in the depth of the arc produce large differences in the calculated radius. Suppose the surface is slightly uneven, the measuring points are a few millimeters off, or the line chosen as the original edge is actually a later fracture. The estimated disc diameter can change considerably. Dunn himself described some measurements as approximate and noted irregularities in the block. That does not invalidate the calculation, but it means the 11-meter figure should be treated as a reconstruction rather than an established measurement of an ancient machine. A three-dimensional scan could test whether the surface is truly part of a cylinder. If thousands of measured points fit one consistent radius, the case for controlled geometry would become stronger. If the radius changes gradually or differs across small areas, the surface may have been formed by repeated grinding rather than one rotating blade. The scan could also reveal whether the termination curve shares a geometric relationship with the main concavity. Dunn's theory predicts that the two radii should be compatible with a single tilted cutter of a particular size. If precise data show that no common tool geometry fits them, the large disk model would weaken. If the predicted relationship appears with very small deviation, the block would become much harder to explain casually. Material analysis would help in a different way. Granite is not uniform. A cutting tool may slow when it encounters a large quartz crystal, Move more quickly through feldspar and pull mica from the surface. Loose abrasive and fixed teeth may leave different microscopic damage around those minerals. Under magnification, researchers could look for crushed crystal edges, directional polishing, embedded copper, residual abrasive, repeated impact marks, or fractures consistent with weathering. Modern experimental cuts could then be made in similar granite using several possible methods. One test might use a straight copper saw with dry quartz sand. Another could use wet abrasive slurry. A third could place the saw in a rigid wooden frame. A fourth could use a pendulum-mounted blade. Smaller rotating cutters could be tested at different angles, followed by grinding and finishing. The objective would not be to make something vaguely similar. It would be to reproduce the same combination of geometry and microscopic marks. Scale would still have to be considered. A small rotating disc may create the same mathematical curvature as a large one, only if the block or cutter follows a carefully controlled path. A full-size experimental saw 11 meters across would be expensive and difficult to build, but researchers could begin with structural calculations and scaled models. Those calculations might reveal whether a wooden wheel with a segmented cutting rim was possible. The device would not necessarily require a solid metal disc. A large timber frame could support replaceable copper or stone cutting elements around its edge. Ancient builders used substantial wooden structures in ships, doors, sledges, and lifting arrangements, so a framed wheel is not beyond imagination. Imagination, though, must be followed by evidence. A segmented wheel should leave a characteristic rhythm of marks as each cutting element passes. Wear might produce repeating variations at intervals related to the spacing of the segments. The cut might show changes when one element broke or became dull. A continuous copper rim with loose sand would leave a different pattern. A straight drag saw would produce another. If the block preserves repeated cycles that match the circumference or segment arrangement of a rotating tool, that would be important. So far, the published claim focuses mainly on visible parallel striations and calculated radii rather than a demonstrated repeating tooth pattern. Powering such a device also presents options. Human workers could turn a large wheel through ropes, treadles, cranks, or attach beams. Counterweights might help maintain motion. Water power is sometimes suggested, although there is no accepted evidence of water-driven stone saws in Old Kingdom Egypt, and the Abu Rawash location would make a reliable water supply to the elevated machine especially awkward. Animal power might be considered, but again the support system and transmission would need to be reconstructed. Slow rotation is not automatically a problem. A blade more than 11 meters in diameter covers a long distance at its rim with each turn. Even a few rotations per minute would give the cutting edge substantial linear movement. The greater challenge would be maintaining stiffness and controlling the feed. If the blade wobbled too much, the kerf would widen, the cutting elements would bind, and the surface would become irregular. Dunn interprets slight wandering as limited wobble, but the proposed machine would need to be stable enough that the wandering remained coordinated across a broad area. A giant saw is therefore physically imaginable. That statement is much weaker than saying it existed. Engineers can design several devices capable of producing the block's approximate shape. Archaeology asks which design, if any, is supported by remains from the site, and by consistent traces on other objects. At present, Abu Rawash has not produced a recognised wheel bearing, mounting structure, segmented rim, drive mechanism, or collection of specialised components belonging to such a saw. Dunn suggested that long trenches traditionally interpreted as boat pits might have held large cutting machines. The idea offers a possible mounting space, but the trenches have not yielded mechanical fittings that establish this use. Boat pits are well known in Egyptian royal complexes. Some contained actual wooden boats, while others may have held symbolic vessels or represented ritual features. Reinterpreting them as machine foundations would require evidence that distinguishes a saw installation from a boat-related structure. Suitable evidence might include bearing sockets, repeated wear at points where an axle turned, anchor holes positioned for tensioning ropes, stone surfaces damaged by a rotating frame, metal fragments, abrasive deposits, or unfinished blocks arranged in relation to the trench. Without these, placing an imagined saw in a conveniently sized depression is possible, but not conclusive. The absence of surviving equipment does not settle the matter either. Wood, rope, and leather decay. Copper was valuable and frequently recycled. A machine could be dismantled after construction. Later quarrying might destroy foundations and scatter the remaining pieces. Still, when a theory proposes equipment on a monumental scale, investigators reasonably expect more than one ambiguous surface. Large machines require organized space, maintenance, replacement parts, skilled operators, and supplies of abrasive. Even if the main structure vanished, the production system should leave patterns in workshops, waste, unfinished stones, and tool marks across multiple objects. This is why the curved block cannot be studied in isolation. Its strongest possible support would come from similar surfaces at other Egyptian sites. If blocks at Giza, Abu Rawash, Karnak and elsewhere preserve the same compound geometry, the same line spacing, the same coordinated wandering, and the same multi-stage steps, a shared machine becomes easier to argue. If the comparisons show only general scratches and curves of different kinds, the case becomes weaker. Ancient stoneworking involved many techniques, and similar-looking marks can emerge from unrelated processes. The Abu Rawash block remains useful because it turns a broad argument into something measurable. Instead of asking whether ancient Egyptians had advanced technology, we can ask whether the main surface fits one cylinder, whether the end curve shares a centre with it, how far apart the lines are, whether those intervals remain constant, and which marks cross one another. We can also ask which feature came first. At several points on the block, the surface appears to change level. One area has been described as a step located a short distance from the broken end. If the step belongs to the original working process, it may record a change in tool angle or a separate pass. A straight saw working with a loose abrasive can leave ridges when the blade shifts position. Grinding can produce shallow ledges when one area receives more work than another. A rotating cutter can leave a step when the feed changes. The step is therefore significant, but only when its full geometry is recorded. There is another possibility that deserves attention. The block may have been a failed piece. A tool could have wandered, cut too deeply, or produced a surface outside the intended shape. Workers may then have abandoned it or broken it for reuse. This could explain why such an unusual form survives while cleaner examples are difficult to find. Finished objects were polished, installed, damaged or removed. A rejected object may preserve the manufacturing error that reveals the process. A failure also changes how we judge precision. The regular areas may show what the tool normally did, while the uneven sections record loss of control. Dunn sees coordinated wandering in the striations and interprets it as the wobble of a rotating blade. Another investigator might see the same feature as movement of a hand-guided abrasive tool. To decide between them, we need to look much more closely at the lines themselves, their spacing, depth, direction, and relationship to the granite crystals form the next part of the argument. The broad concavity suggests the path of a tool, but the fine marks may tell us what was actually touching the stone while that path was made. Those fine marks are often called striations, and they are among the most important features on the Abu Rawash block. They appear as narrow lines running across parts of the worked granite surface. Some are easy to see when the light strikes from the side. Others become less obvious when the stone is viewed from directly above. Their spacing seems fairly regular in certain areas, and several lines appear to change direction together as they travel across the surface. Supporters of the machining theory describe these as feed lines. In modern manufacturing, a feed mark can be created when a cutting tool moves across a workpiece at a controlled rate. A rotating cutter completes one turn, advances slightly, completes another turn, and leaves a repeating pattern. If the rate of advance and the speed of rotation are known, the spacing between marks can provide information about how the machine operated. That is useful in a modern workshop because the machine and its motion are already understood. When the only surviving evidence is an ancient stone, the same word can create a false sense of certainty. Calling a line a feed mark does not prove that it records one revolution of a powered cutter. Before the spacing can be used to calculate speed, pressure, or cutting rate, investigators must establish what produced each line and how the tool moved. A straight saw dragged back and forth may leave repeated scratches. A rotating blade may leave curved grooves. A grinding tool can create overlapping lines. Loose grains of abrasive trapped under a blade can score the surface for several centimetres before breaking or becoming dislodged. Later polishing may remove the shallower scratches and leave only the deepest ones, making the surviving pattern look more regular than the original surface. The Abu Rawash lines are especially interesting because some appear to wander together. Instead of remaining perfectly straight, they shift slightly to one side and then return. Christopher Dunn interpreted this coordinated movement as evidence that the cutting points were fixed to the same tool. If several teeth or embedded cutting elements were attached to a rigid blade, a small wobble in that blade could cause all their paths to move together. He also reported narrow, closely spaced grooves on the surface and treated them as part of a controlled mechanical cut. The argument sounds straightforward. Independent grains of loose sand should move independently. Fixed teeth should move together. If the grooves wander together, fixed teeth seem like the better explanation. The problem is that loose abrasive does not always behave as a collection of completely independent particles. A soft metal blade pressed against granite can temporarily hold hard grains in its surface. Quartz particles can become embedded in copper and remain there through part of a stroke. During that time, they behave like small cutting points. The groove already formed by the saw also guides both the blade and the abrasive, encouraging later particles to travel along similar paths. A wooden or metal frame can add further control. If the blade bends or shifts, the entire contact zone may move slightly. Several abrasive grains can then leave scratches that change direction together, even though they were never permanently mounted as teeth. Coordinated lines may indicate a guided tool, but they do not automatically identify a toothed circular saw. Dennis Stocks tested reconstructed copper saws and drills on Aswan granite using abrasive material. His experiments demonstrated that granite could be sawn and drilled with copper, acting as the carrier, while harder grains performed much of the cutting. The work was slow, the copper wore down, and maintaining the abrasive was labour-intensive, but the process produced actual cuts in rose granite rather than merely polishing the surface. The experimental results are important because they remove one common objection. Copper does not have to be harder than granite if the copper is not doing all the cutting. A copper saw can press quartz-rich abrasive against the stone. The harder grains scratch, crush and remove small particles from the granite, while the softer copper holds them and moves them through the kerf. This does not mean that any line in granite can be explained by saying copper and sand and then moving on. The method must still account for the shape, spacing, depth, and continuity of the marks. A successful experiment should produce a surface that can be compared directly with the ancient one. That comparison becomes difficult because the word striation covers many different features. One mark may be a shallow scratch only a fraction of a millimetre deep. Another may be a narrow groove with raised edges. A third may actually be the boundary between two slightly different surface levels. Photographs often place all of them in the same category because they look like lines. Their cross-sections matter. A fixed, sharp point dragged through stone may leave a V-shaped groove. A rounded, abrasive grain may create a broader U-shaped channel. Repeated grinding can flatten the bottom. Brittle minerals may fracture along the sides, while softer components may smear or crumble differently. Granite adds another complication because it is not one uniform material. The cutting tool passes through quartz, feldspar, mica, and smaller mineral inclusions. Quartz is hard and brittle. Feldspar is slightly softer but still resistant. Mica forms thin sheets that can pull away from the surface. A single groove crossing all three may change shape as the material changes. Alternative researchers argue that some Egyptian grooves pass through quartz and feldspar with little visible difference. They take this as evidence that the cutting point was extremely hard and operated under controlled pressure. Similar observations were made by Flinders Petrie in the 19th century. Petrie examined sawn pieces, drilled holes and granite cores from Giza, and argued that some deep regular grooves could not be explained by loose abrasive alone. He proposed bronze tools fitted with cutting points harder than quartz, and even identified one diorite fragment as evidence of a circular saw. Petrie's description is often presented as though it settles the modern debate. It does not. He was an exceptionally careful surveyor, but he was working before later experimental programs had tested many abrasive methods in detail. His conclusion was an interpretation of the marks, not the discovery of an actual jeweled saw blade. It is still worth taking seriously because Petrie recorded features that remain difficult to discuss. On one granite drill core, he measured a spiral groove that appeared to descend rapidly around the core. He believed the rate was too great for ordinary loose abrasive and suggested enormous pressure or fixed cutting points. On other pieces, he reported regular arc-shaped grooves and abandoned saw cuts. The debate has therefore existed for well over a century. It did not begin with internet videos, and it cannot be resolved by dismissing every unusual mark as a recent invention. Early archaeologists themselves noticed that some surfaces looked surprisingly mechanical. The disagreement concerns which mechanical process produced them. The Abu Rawash block adds compound geometry to the problem. The main worked surface is broadly concave, but the boundary between the smooth and rough areas also forms an arc. At least 2 small changes in level have been described on the smoother region. These features have been interpreted as separate cutting passes. Imagine a large circular blade entering a stone at an angle. The rim cuts a curved path. As the stone or blade advances, the cutting surface sweeps across the block. If the angle changes, the next pass does not perfectly match the first. A narrow step remains where the surfaces meet. If the blade moves sideways under load, the scratches produced by its cutting points shift together. This model explains several observations with one machine. It explains the concavity through the radius of the blade. It explains the terminating arc through the edge of the rotating cut. It explains the steps through changes in blade position. It explains the striations through teeth or fixed abrasive points. A model that explains several details at once is usually preferable to one that invents a separate cause for every mark. It is also more vulnerable to testing. If one tilted circular blade produced the surface, the different curves should follow a consistent geometric relationship. Their radii, centres and angles should agree within a reasonable margin. The existing measurements are not detailed enough to establish that relationship beyond dispute. The proposed diameter of more than 11 metres was calculated from limited measurements on an irregular damaged block. Extending a short arc into a full circle can magnify small errors. A difference of only a few millimetres in the depth of the curve can produce a significant change in the estimated radius. A slightly uneven measuring point, an eroded edge, or a camera angle can alter the result. This does not make the calculation meaningless. It means that the number should be described as a possible fit rather than the measured diameter of a known ancient saw. The ending arc creates a similar problem. It may represent the point at which a rotating cutter left the stone. It may also mark where a later operation stopped. A worker grinding one region more heavily than another could leave a curved boundary if the grinding tool was swung around a fixed point. A fracture following stress in the block might expose part of an older worked surface and create an apparently deliberate edge. The correct sequence can sometimes be determined by examining which marks continue across others. Suppose the fine striations run uninterrupted over one of the steps. That would suggest the step existed before the striated pass. If the lines stop at the step and resume at a slightly different angle beyond it, the two areas may record separate operations. Where a polished area crosses a deeper groove, the groove may be older if its edges have been softened. A A sharp groove cutting through a weathered surface is probably later. These relationships are basic archaeological tools. They allow investigators to build a relative sequence even when no absolute date is available. Unfortunately, the published images of the Abu Rawash block do not provide enough resolution and controlled lighting to map every crossing. Some photographs show the lines clearly, while others make the same region appear almost smooth. Measurements have been reported by supporters of the machine interpretation, but there is no widely available independent three-dimensional survey with microscopic surface data. That missing documentation matters because extraordinary-looking cuts can become less extraordinary when viewed from another angle. It can also work in the opposite direction. A surface that seems roughly shaped in a normal photograph may reveal highly regular toolpaths under scanning. The ideal study would begin by cleaning the stone only through approved conservation methods without grinding or altering the surface. Investigators would place permanent reference points around it and scan the entire object at high resolution. The result would be a three-dimensional model accurate enough to measure shallow grooves, curvature, and surface steps. Each visible line could then be traced. Researchers could test whether the lines are equally spaced, whether they remain parallel, and whether their side-to-side movement is genuinely coordinated. They could calculate how many separate families of marks are present and identify the order in which they were made. A tool moving in one direction may leave lines at one angle. A later finishing operation may cross them at another. Weathering may produce short, irregular cracks that ignore both. What looks like one complicated machine operation could turn out to be three simpler processes superimposed on the same stone. The reverse is also possible. Lines that seem random to the eye may follow a consistent repeating interval when measured digitally. If the same spacing appears across a large area, and the grooves share a common shape, the case for a controlled cutting edge becomes stronger. Frequency analysis could be useful. Modern engineers examine repeating surface patterns to identify vibration, rotation, and feed. If a tool wobbles once per revolution, the marks may contain a regular wave. If several teeth are unevenly spaced, a repeating sequence may appear each time the blade completes a turn. A large circular saw would be expected to produce some form of repetition, unless its cutting edge used completely loose abrasive. The length of the repeating cycle would depend on the blade's circumference, the number of cutting points, the rotational speed, and the movement of the stone. Finding such a cycle in the Abu Rawash surface would not tell us what powered the machine, but it would provide stronger evidence of rotation. Failing to find one would not disprove rotation, because later grinding and weathering may have removed it. Still, it would limit what can safely be claimed. The arcs deserve the same measured treatment. A true circular arc has a constant radius. A hand-ground curve may look circular over a short distance, while varying when measured point by point. A swinging tool attached to a rope or rigid arm can also produce a circular path, but its radius would reflect the length of the arm rather than the size of a rotating blade. This introduces an alternative that is often missed. A large circular cut does not always require a complete circular saw. A cutting or grinding head mounted at the end of a long beam could sweep through an arc. The beam might pivot around a fixed support while workers pulled it back and forth. Such a device could create a broad, curved surface using a much smaller cutting element. A pendulum-mounted saw could do something similar. The blade would swing through a curved path while abrasive removed the stone at the lowest part of the motion. Adjusting the pivot or moving the block could create overlapping concave cuts. The machine would still be substantial, but it would not require an 11-meter metal disc. There are difficulties with this model as well. A swinging straight blade usually creates a cylindrical curve in one main direction. Producing compound curvature would require additional movement or a change in the pivot. The resulting striations might follow the swing rather than the proposed feed direction. Once again, the surface mark should distinguish between the possibilities. A smaller rotary grinder attached to an arm could create complex forms, but there is no direct archaeological evidence for such a device at Abu Rawash. It is offered here not as the correct answer, but as a reminder that geometry can often be generated by more than one mechanism. Machinists know this well. A curved surface can be produced by a tool with the same curve, by a smaller tool following a programmed path, by moving the workpiece, or by combining rotations. Looking only at the finished shape may not reveal which method was chosen. Errors can provide better evidence than intended surfaces. The Abu Rawash steps may be examples of such errors. If a blade entered too deeply and was then withdrawn, the overcut could preserve its radius. Petrie described comparable mistakes at Giza, including saw cuts that ran too far into granite and were backed out. He also documented basalt and diorite pieces bearing regular grooves and abandoned cuts. An overcut made with a straight blade normally continues as a straight kerf unless the blade bends or rocks. An overcut made by a circular blade produces an arc determined by the disc. An overcut made by a swinging tool creates a curve based on the pivot. These accidental marks can therefore act as partial signatures of the machine. Yet even an arc-shaped overcut must be examined in 3 dimensions. A straight saw moving in a rocking action can leave a curved bottom. Anyone who has used a longhand saw knows that the blade does not always travel as a perfectly level line. Workers may deliberately rock it to concentrate pressure on a smaller region, deepen the cut, and help abrasive reach the working face. A flexible blade can also bow. If pressure is uneven or the kerf narrows, the middle of the blade may bend sideways or downward. The resulting surface can be concave. Dunn argues that the particular Abu Rawash geometry cannot be explained by simple bending, but that claim has not been settled through published full-scale comparison tests. Testing blade bending would not be especially glamorous, but it would be useful. Researchers could build copper or bronze saws of different lengths and thicknesses, mount them in wooden frames, vary the tension, and cut granite using several abrasive mixtures. They could deliberately allow the blades to wander, rock, and bind. The failed cuts would be more informative than the successful ones. Investigators could compare the resulting steps and curves with the ancient surface. If flexible straight saws consistently produce the same geometry, the giant circular blade becomes unnecessary. If they fail despite realistic variations, the mechanical question becomes harder. The composition of the abrasive should also be varied. Sand is not a single standard material. Nile sand, desert sand, crushed quartz, emery, corundum-rich material, and mixtures of different grain sizes behave differently. Angular grains cut more aggressively than rounded ones. Water changes how particles move and how waste leaves the kerf. Oil or other liquids could alter friction, although evidence for their use would need to be established. Experimental results based on one copper blade and one bag of modern sand cannot represent every ancient method. Egyptian craftspeople may have selected, crushed, washed, and graded abrasive deliberately. A specialist workshop could improve cutting speed through experience without possessing any unknown source of power. The same point applies to the word primitive. A copper blade operated by hand can be part of a sophisticated system. The frame, weights, guides, abrasive supply, tension control, and work sequence may matter more than the blade material. Describing the method only as copper and sand is like describing a sailing ship as wood and cloth. Accurate certainly, but not enough to explain how it crosses an ocean. The machining hypothesis draws strength from the impression that all these controls must have existed in a much more advanced form. The regular lines, smooth mineral cuts, arcs, and apparent multi-stage passes seem to show a tool moving with confidence through hard granite. That impression should lead to measurement rather than immediate certainty. A surface can look highly regular because human vision focuses on the strongest surviving pattern. Shallow irregular marks fade into the background. Deep parallel ones remain visible. Thousands of years of weathering may perform a kind of selection, preserving some traces and removing others. Lighting can then turn that selected pattern into something that resembles a modern milled finish. The resemblance may be meaningful, but resemblance alone is not identification. The strongest claim would be that the Abu Rawash striations have a measurable structure that known abrasive methods cannot reproduce. To demonstrate that, investigators would need to publish the ancient measurements, define the distinguishing features in advance, and compare them with blind samples made by different tools. Experts examining the samples should not know which surface is ancient, which was made with a framed copper saw, which came from a rotating modern cutter, and which was ground by hand. They would classify the marks using the same criteria. That would reduce the risk of finding a machine only when one is expected. Until such tests are performed, the lines remain evidence of controlled stoneworking but not proof of a particular machine. The arcs show that material was removed along curved paths, but they do not yet establish an 11-metre disc. The steps suggest more than one operation, or a change in the tool's position, but the exact sequence remains open. Nothing about that uncertainty makes the block unimportant. It makes it more useful. The stone gives us specific questions that can be tested. It also forces both sides of the argument to move beyond general statements. Those proposing a lost machine must show that the marks contain features unique to their mechanism. Those defending copper saws and loose abrasive must demonstrate that the method can create the same compound surface, not merely a narrow groove in granite. That brings us to the central practical issue. We know that copper and abrasive can remove granite. What we do not yet know is whether they can do so with the speed, control, geometry and surface character required to explain the Abu Rawash block and the related marks found elsewhere in Egypt. To answer that, we need to look closely at what copper tools can actually do, what their limits are, and whether those limits have sometimes been described more confidently than the experiments allow. The limits of copper tools are often presented as the simplest part of this mystery. Copper is soft, granite is hard. Therefore, we're told, copper cannot cut granite. The conclusion sounds obvious until we look at what the copper was expected to do. An ancient saw did not need to slice directly through every mineral in the stone. It could carry abrasive grains across the surface while pressure and movement allowed those grains to remove material. In that arrangement, the copper provided shape and control. The abrasive did most of the cutting. This basic principle is still used in many forms of manufacturing. A softer material can carry harder particles and use them to grind something that would resist the carrier on its own. A polishing cloth is softer than metal, but polishing compounds held by the cloth can alter the metal surface. A wire carrying abrasive slurry can cut stone even though the wire itself is not harder than every mineral it encounters. The statement that copper is softer than granite is therefore correct but incomplete. It tells us why a bare copper edge would perform poorly. It does not tell us what happens when quartz grains, crushed stone or another abrasive are placed between the copper and the granite. Experimental archaeologist Dennis Stocks conducted practical trials on rose granite at Aswan, using reconstructed tools and abrasives. His tests included sawing, drilling, cutting and surface working operations. They demonstrated that copper tools combined with abrasive material could remove granite, although the work was slow, physically demanding and destructive to the copper. The experiments did not make granite easy to work. They showed that it was possible to work it with materials available in ancient Egypt. A copper saw can be imagined as a long strip of metal held by one or more workers. Abrasive is added to the cutting area, sometimes with water to help carry loose particles and remove waste. The saw is pulled back and forth. Pressure forces grains against the granite. Some roll, some crush, and some become embedded in the softer copper. An embedded grain can act like a temporary tooth. It scratches the stone until it breaks, becomes blunt, or falls out. New grains take its place. The process repeats thousands of times. This helps explain why an abrasive saw may leave lines that look more organized than a loose pile of sand would suggest. The grains are not floating freely over an open surface. They are confined beneath a blade and inside a developing groove. Once a kerf begins, its walls guide the saw. The blade guides the abrasive. Existing scratches can guide later grains along similar paths. The deeper the cut becomes, the more controlled the direction may become, provided the blade remains tensioned and the workers keep the motion steady. A wooden frame could help maintain alignment. Weights could provide consistent downward force. Workers could concentrate on pulling the saw while another person supplied abrasive and water. None of those components is especially mysterious. Together, however, they form a working system rather than a simple piece of copper being rubbed against stone. The rate of cutting is where objections usually return. Experimental sawing of granite is slow. A team may work for hours and produce only a shallow groove. Large Egyptian monuments contain enormous quantities of worked stone. Granite boxes, statues, columns, doorways, and architectural blocks sometimes show extensive cutting. Critics ask whether a slow, abrasive process could produce all of that work within a realistic construction schedule. This is a fair question, but it cannot be answered by taking the output of one small modern experiment and multiplying it across an entire monument without adjustment. Experimental archaeologists are usually learning the method as they perform it. Ancient specialists may have worked with these materials for years. They may have selected abrasives carefully, adjusted water content, altered the blade shape, changed the weight, and developed workshop routines that increased efficiency. A modern test may also use a short blade, a limited number of workers, or an abrasive that differs from the ancient material. Sand varies greatly. Rounded desert grains do not behave like freshly crushed quartz. Fine particles may polish instead of cutting. Very large particles may roll or jam. A mixture with the correct grain size could perform better than whatever happened to be available during a single demonstration. The word sand creates an image of someone collecting a bucket from the nearest dune. The actual abrasive may have been selected, crushed, washed, sorted, and replaced regularly. It could have included quartz-rich material or harder minerals obtained through trade or quarrying. A specialized workshop would have learned which mixture cut quickly and which one produced a smoother finish. The Egyptians did not need a modern understanding of mineral hardness to notice that one powder worked better than another. Repeated practical experience would be enough. A craftsperson does not need to write a geological paper before deciding that the sharp, pale grains from one location cut better than the rounded brown grains from another. Copper itself could also vary. Pure copper is relatively soft, but hammering changes its condition. Alloying copper with arsenic or tin can change hardness and wear resistance, depending on composition and treatment. The available archaeological record does not support assuming that every Egyptian saw was made from the strongest possible alloy, but neither should every tool be imagined as a weak strip of untreated metal. The metal did not need to remain sharp in the way a modern steel saw does. It needed to survive long enough to hold shape, carry abrasive, and be repaired or replaced. Copper wear was not necessarily a failure of the process. It may have been an expected cost. If a blade became thinner or uneven, workers could hammer it, straighten it, or recycle it. Copper was valuable, but worn material could be melted and reused. A large building project could maintain a supply of blades in the same way a modern construction site maintains drill bits and grinding discs. The difference is that almost all of that metal would later be recovered, leaving very little for archaeologists. The surviving evidence for ancient Egyptian saws includes artistic scenes, tool fragments, cut surfaces, and traces of copper compounds in some worked areas. Flinders Petrie examined numerous marks at Giza and accepted that bronze or copper-based saws were involved. He reported green staining in some saw cuts and described blades of different thicknesses, including long straight saws used on large granite objects. Petrie did not believe loose abrasive explained every example he studied. He proposed that some tools carried fixed cutting points harder than quartz. He considered materials such as corundum or diamond because certain grooves appeared too deep or regular to him for ordinary abrasive powder. That difference is important. The historical argument is not simply Petrie on one side and modern alternative researchers on the other. Petrie himself thought the Egyptians possessed highly capable cutting tools. What remains uncertain is whether his proposed fixed cutting points were necessary, whether they were correctly identified from the marks, and whether later abrasive experiments provide a better explanation. No dual-set ancient saw has been recovered from a secure Egyptian context. There are hard minerals that could potentially serve as cutting particles, but a complete blade with regularly mounted teeth has not been found. Petrie inferred the cutting points from the work. The same caution applied to the Abu Rawash machine must therefore apply here. A hard groove can suggest a hard cutting point, but the point may have been fixed permanently, embedded temporarily in copper, or dragged through the cut as loose abrasive. One way to distinguish these processes is to examine the line spacing. Permanently mounted teeth should remain at fixed distances from one another. If several teeth leave grooves, their spacing should repeat. A broken tooth might produce a missing line. A projecting tooth might create a deeper groove each time the blade moves. Loose abrasive should produce a less stable pattern. Individual grains break, shift, and fall away. Some remain embedded briefly, but their positions change as the copper wears. The scratches may be generally parallel without maintaining the same exact spacing over a long distance. This sounds like a decisive test, but ancient surfaces are rarely clean enough to make it easy. A saw may pass over the same region thousands of times. Later strokes erase or deepen earlier scratches. Grinding may remove part of the pattern. Weathering may widen some grooves and destroy others. The lines visible today are not necessarily a complete record of every cutting point. They are the parts that survived. The mineral structure of granite can also organize the damage. A grain may travel smoothly through feldspar, then fracture a quartz crystal, then skip across a mica boundary. Another grain may enter the same weak path on a later stroke. Repeated failure along mineral boundaries can create lines that appear linked even without evenly spaced teeth. For this reason, microscopic comparison is more useful than visual similarity. Researchers can examine groove shape, fractured crystal edges, polishing direction, embedded residues, and damage beneath the immediate surface. A loose grain rolling under pressure may crush the stone differently from a fixed sharp point. A rotating blade may leave a different directional pattern from a reciprocating one. The trouble is that large systematic comparisons are still limited. Stocks demonstrated that reconstructed tools could saw and drill granite, but the existence of a workable general method does not mean every disputed Egyptian surface has been replicated. The Abu Rawash block is not merely a straight groove cut into a granite slab. It has a broad concavity, curved boundaries, fine lines, and apparent changes in level. A standard experiment showing that a straight copper saw can enter granite answers only the first question: can the material be cut? It does not answer whether that particular form can be produced with the proposed toolkit. A convincing replication would need to begin with similar granite. The block should have comparable mineral grain size and composition. The experimenters would then use reconstructed copper tools, abrasives available to ancient workers, and a support system built from plausible materials. They would need to produce the main concavity, not by manually grinding it afterward until it looked close enough, but through a documented sequence. Every stage should be recorded. The final surface should be scanned and compared with the ancient block using the same measurements. If a straight-framed saw can create the compound curve by rocking, bending, or changing angle, the test should show exactly how. If the process leaves steps, the positions and shapes of those steps should resemble the ancient ones. If it creates parallel striations, their spacing and cross-section should be measured. Without this, the conventional explanation risks becoming too flexible. A straight saw explains one line. Grinding explains the curve. Blade movement explains the step. Weathering explains the irregularity. Polishing explains the missing marks. Each element may be reasonable on its own, but combining them after seeing the object can produce an explanation that is difficult to disprove. The machine theory faces the same danger. When blade wobble explains one feature, a change in angle explains another, and later damage explains anything that does not fit. A useful reconstruction must limit its own freedom. It should predict what the surface will look like before the test is performed. Pressure is another disputed issue. Petrie believed some drill grooves indicated a rapid advance into granite, and concluded that very high force must have been applied. Alternative researchers have continued this argument, claiming that manual copper tools could not remove enough material per revolution to match the surviving spirals and lines. The phrase per revolution already assumes that each visible groove corresponds to one complete turn. That assumption may be wrong. A spiral-looking mark could contain the paths of several abrasive grains formed over many rotations. One deep line may survive while dozens of shallower lines disappear. Measuring the pitch of the surviving groove does not necessarily reveal how far the drill moved during one turn. Stocks's drilling experiments were designed in part to examine such claims. Tubular copper drills used with abrasive can cut circular channels and leave cores. Movement of abrasive beneath the tube can produce grooves on both the hull wall and the core. The resulting patterns may appear more aggressive than a simple calculation based on soft copper would suggest, because the grains are doing the cutting. This does not settle every famous drill core. Some examples still deserve better scanning and independent testing. It does show why a dramatic feed rate should not be calculated from one visible spiral until the mechanism that produced the spiral is established. A similar warning applies to the Abu Rawash striations. If each line is assumed to represent one tooth or one revolution, the implied machine can become very powerful. If the lines formed gradually through repeated abrasive strokes, the implied rate becomes much slower. The marks do not arrive with labels. The interpretation creates the machine parameters, and those parameters are then sometimes presented as proof of the interpretation. There is also the question of surface finish. Abrasive sawing tends to leave a rough face requiring further dressing. Many ancient Egyptian granite surfaces were eventually smoothed or polished. Workers may have moved from pounding to sawing, then to coarse grinding, fine grinding and polishing. The final result can hide the earlier operations. A polished box tells us little about the exact appearance of the first cut. Unfinished objects are more useful, but they may represent stages that were never intended to be precise. The curved Abu Rawash surface may have been an intermediate stage. If it was going to be ground further, its current geometry may record efficient bulk removal rather than the intended final form. Workers might tolerate ridges, steps, and tool wandering, because those defects would disappear during finishing. This reduces the need for the initial cutting process to produce a perfect surface. It does not remove the need to explain the observed curvature. A long straight saw can create a curved bottom if it is rocked during use. Workers often move a handsaw through an arc, rather than keeping the blade perfectly horizontal. Rocking concentrates force on a smaller part of the cutting edge. It can help abrasive enter the kerf and prevent the full blade from binding. Repeated rocking naturally deepens the centre more than the ends. If the saw is also allowed to bend, the surface may become concave across another direction. Moving the block or altering the saw angle between passes can add a second curve. That sounds capable of producing almost anything, which is precisely why it must be tested. Copper blades of realistic thickness should be placed under realistic tension. The degree of bending should be measured. Researchers should determine whether the blade can create the required radius without folding, binding, or widening the cut beyond what is seen at Abu Rawash. A short modern demonstration in soft stone would not be enough. The experiment needs granite, long working times, and the same scale of motion. Grinding offers another possible route. A hard stone tool with abrasive beneath it can be pushed or swung over a surface. If attached to a long arm pivoting from one point, it can generate a broad arc. The radius would come from the arm, not from a giant wheel. Workers could lower the tool gradually and move the block between sessions. A controlled grinding rig might leave parallel scratches and compound curvature without using a circular saw. It would still count as a machine, but one built mainly from wood, rope, stone and copper rather than a vast metal disc. The conventional and alternative positions may therefore be closer than they first appear. One side imagines simple hand tools, the other imagines powered industrial equipment. Between them lies a wide range of guided mechanical systems. A large wooden frame with weights and abrasive-fed copper blades would be more advanced than two workers holding a loose strip of metal. It would also be compatible with materials known in ancient Egypt. Such a system could be forgotten because its wooden structure decayed and its copper parts were recycled. The question is not whether Egyptian workers use bare hands or modern electric motors. It is how much guidance, leverage, tension, rotation, and mechanical control they incorporated into their equipment. Scale complicates the labour argument as well. A slow saw can still remove a large amount of material if many saws operate at once. Royal projects had organised workforces, supply systems, and skilled crews. A block might spend weeks at a quarry or workshop before reaching the building site. Modern viewers often imagine that every stone had to be completed in immediate sequence. In reality, several stages could overlap. Quarry workers extracted new blocks, while transport crews moved earlier ones, and finishers worked on stones already delivered. A cutting rate that seems frustrating for one person may be acceptable within a production system. Anyone who has watched a printer produce one page at a time knows that slow individual actions can still build a very large pile, particularly when someone has unwisely selected print all. The real labour calculation requires the number of hard stone objects, the amount removed by sawing rather than pounding, the number of available workers, the duration of construction, and the efficiency of the workshop. Most popular arguments use only one or two of those values. They may calculate how long it takes one modern person to saw a groove, then compare that with the total mass of a pyramid, even though most pyramid stone is limestone, and much of it was not cut with copper saws. Or they may point to the entire reign of a king without accounting for quarrying, transport, seasonal labour, and simultaneous work. A better estimate would focus on one object. How much granite had to be removed from a sarcophagus? Which parts could be split or pounded away? Which required sawing? Which required drilling? How many tools could work on it at once? How much time did polishing add? Only then can we decide whether the process is merely slow or impossibly slow. Tool wear must be calculated in the same way. Copper loss during abrasive sawing can be significant. That creates a demand for metal, fuel, casting, hammering, repair, and recycling. If the required amount exceeds what could reasonably be supplied, the method weakens. If the worn copper remains in the slurry and can be collected, or if blades are repaired repeatedly, the demand may be less severe. Actual workshop experiments should measure this rather than assume it. The absence of large numbers of surviving saws is not surprising. Copper was too useful to leave inside an abandoned workshop. Worn tools could become new tools, fittings, vessels, or raw material. A stone hammer may be discarded when broken. A damaged copper blade is still copper. This helps explain why tool marks can survive more readily than tools. It does not excuse the total absence of every proposed component. If fixed jeweled teeth were widely used, we might expect some teeth, mounting fragments, workshop debris, or distinctive unfinished blades. If enormous circular machines were common, we might expect support features and repeated wear patterns. The abrasive method has one advantage here because most of its system uses materials that are either common, recyclable, or perishable. Copper disappears into later metalworking, wood and rope decay, sand returns to the ground, the granite cut remains. Its other advantage is direct experimental success. We know the method can cut the stone. The outstanding issue is not possibility but adequacy. Can it produce the Abu Rawash block's broad hollow efficiently? Can it maintain the apparent regularity of the striations? Can it create the terminating arcs and steps? Can it explain similar marks on granite and basalt at Giza and other sites without requiring a different special method for each object? At present, The most careful answer is that copper and abrasive are capable of far more than the simplest objection allows. They can saw granite, drill it, grind it, and leave organised marks. Experimental work has established that much. The same experiments have not reproduced every claimed feature on every disputed artefact. They do not provide a complete explanation of the Abu Rawash geometry. Saying that copper and sand could cut granite is therefore justified. Saying they have already explained the entire block is not. There may have been better abrasives, more efficient frames, heavier pressure systems, longer blades, or specialised movements not yet tested. Those additions would still belong to ancient mechanical technology. They would not require electricity, steel, or a lost global civilization. But if realistic abrasive systems repeatedly fail to produce the compound curves and coordinated marks, another class of machine must be considered. The most dramatic proposal is the one already suggested by the block's reconstructed radius, a rotating cutter whose diameter was not 2 meters or 3 meters, but roughly 11. Before deciding whether such a saw was impossible, practical, or simply the wrong machine, we need to examine what that number actually means, how it was calculated, and what an ancient workshop would have required to build and operate something on that scale. That number, roughly 11 meters, comes from an attempt to reconstruct a missing tool from 2 curves preserved on the granite. It does not come from a surviving blade, a workshop inscription, or a picture of workers operating a large saw. The proposed machine exists because Christopher Dunn measured the block, treated the curved surfaces as sections generated by one tilted circular cutter, and calculated the size of the circle needed to fit them. According to Dunn's published reconstruction, one measured radius was about 23.68 feet, and the other was about 23.95 feet. He proposed that a circular cutter, 37.5 feet, or approximately 11.43 meters, in diameter could produce both curves when tilted at an angle of about 45 degrees. From one direction, the cutting edge would appear circular. From the other, the tilted circle would appear as part of an ellipse. A small section of that combined geometry could match the 2 large radii measured on the block. This is the basic idea behind the 11-meter saw hypothesis. A very large rotating cutter was positioned at an angle. The granite was moved beneath it, the cutter was moved across the granite, or both were moved in a controlled sequence. The rim removed material while leaving the broad concavity, the curved ending, and the fine marks visible on the surface. It is a clever geometric explanation. The question is whether geometry alone can tell us that such a machine really existed. To understand the proposed scale, imagine a circular blade standing upright beside a modern building. An 11-meter disc would be taller than a 3-story house. Its circumference would be almost 36 meters. Even one slow rotation would carry every point on the rim through a considerable distance. A machine of this size would not need to spin like a modern table saw. That would be dangerous, unnecessary, and probably impossible with ancient materials. It might rotate very slowly while its cutting edge ground against the granite. Abrasive could be fed into the contact area, allowing the rim to wear through the stone over many repeated passes. Slow movement does not remove the engineering problems, it merely changes them. The first problem is the blade itself. What was it made from? A solid copper disc 11 meters across would contain an enormous amount of metal. Copper is dense, and a disc thick enough to resist bending would be extremely heavy. If made too thin, it would sag under its own weight. It would flex when pressed against the granite, and its outer edge might move sideways rather than remaining in one controlled plane. A disc does not need to break dramatically to become ineffective. Even a small amount of movement at the centre can produce a much larger displacement at the outer rim. The machine might begin with a cut only a few millimeters wide and gradually wander into a broad, uneven trench. The narrowness and regularity of the Abu Rawash marks are used as evidence that the proposed cutter remained controlled. That means the support system would need to resist both the weight of the disc and the sideways force created during cutting. Making the blade thicker would improve its stiffness, but it would also increase its weight. The frame, axle and bearings would then have to become stronger. More workers or a more powerful drive would be needed to start it moving. Once moving, the large rotating mass would resist changes in speed and direction. A full copper disc is therefore one possible design, but not an especially practical one. A large wooden wheel with a cutting rim is easier to imagine. The central body could be made from heavy timber beams joined into a frame. Copper strips, stone cutting pieces, or replaceable holders could be attached around the edge. The wood would provide the diameter without requiring the entire circle to be metal. Ancient Egyptians built large wooden ships using complicated joints, ropes, planks, and internal supports. That does not prove they built enormous stone saws, but it shows that substantial wooden engineering was available to them. A framed wheel would use familiar materials in an unfamiliar arrangement. The outer edge might carry a continuous copper band. It might carry separate segments. It might simply hold abrasive against the stone while the wooden structure controlled the path. Each design would leave a different surface. A continuous rim used with loose abrasive could produce a relatively uninterrupted cut. Separate cutting segments might leave repeating changes in depth or texture. A missing segment could create a regular gap each time the wheel turned. One projecting piece might score the stone more deeply than the others, leaving a recurring line. If the Abu Rawash block was shaped by a segmented rotating cutter, its surface may preserve such repetition. The spacing between unusual grooves could reflect the distance between cutting elements. A modern scan might reveal a cycle that repeats across the stone. No such repeating cycle has yet been demonstrated in the publicly available measurements. The reported features include parallel striations, slight coordinated wandering, compound curvature, and changes in surface level. Those observations are suggestive, but they do not provide a complete tooth pattern or an identifiable record of individual revolutions. The second major problem is the axle. A wheel more than 11 meters across needs a central support that can carry its weight while allowing rotation. Modern machines use metal shafts, carefully machined bearings, lubricants, and rigid frames. An ancient version would have to achieve the same basic result with wood, copper, stone, grease, and repeated adjustment. Wooden axles can carry heavy loads. Stone sockets can support rotating shafts. Animal-powered mills and large water wheels later operated using combinations of timber, metal fittings, and simple bearings. None of the individual principles is impossible. The difficulty comes from precision. A tiny change at the bearing becomes a larger movement at the cutting edge. If the axle rises, falls, or shifts sideways by a few millimeters, the rim may move by considerably more depending on how the frame flexes. Dunn interpreted slight wandering in the striations as possible blade movement. In his reading, several cutting points shifted together because the whole cutter wobbled. This would not be surprising in a machine of such size. The important question is whether the amount of wobble visible on the stone is compatible with a wooden and copper support system. A machine can wobble and still work. Many traditional devices do not operate with modern precision. The cut only needs to remain within the limits required for the object being made. If later grinding and polishing were planned, the initial saw surface could be rougher than the finished form. The Abu Rawash block may even represent a failed operation. The machine could have shifted, creating a step or cutting at the wrong angle. The stone may have been rejected because the surface was no longer usable. That possibility helps explain why a manufacturing trace survives so clearly. A successful cut might be polished away. A mistake might remain visible because the object was abandoned. It also makes the machine harder to reconstruct. A failed surface does not necessarily show how the equipment behaved under normal conditions. It may preserve the exact moment when something bent, slipped, or came loose. Next comes the question of power. An 11-meter cutter could be moved by people pulling ropes attached to the rim or axle. Workers might walk in alternating groups, turning the wheel a short distance in one direction and then reversing it. a reciprocating rotation would be easier to organise than continuous movement, because the ropes could be pulled back and forth. The cutter might also be turned with long wooden beams extending from the axle. Workers could push the beams as though operating a capstan. Gearing is not essential if the machine moves slowly, although some form of mechanical advantage would reduce the required force. Animal power is another possibility. Cattle or donkeys could walk around a central post while ropes or shafts transmitted movement to the saw. This would introduce additional components and more opportunities for misalignment. Water power is occasionally mentioned in discussions of lost Egyptian machinery, but it is especially difficult at Abu Rawash. The pyramid complex stands on elevated ground northwest of Giza. Supplying a controlled flow of water to power a large wheel that would require substantial hydraulic works, and no accepted archaeological evidence for such a system has been identified at the site. Abu Rawash is documented as a multi-period funerary landscape, including Djedefre's 4th dynasty complex and much earlier 1st dynasty burials, not as the location of a known water-powered industrial installation. Human power remains the simpler proposal. The machine would not need to remove granite quickly. It would only need enough movement and pressure to keep abrasive working along the cutting edge. Suppose the disc rotated once every minute. Its rim would still travel nearly 36 meters during that rotation. Even at this slow speed, a point on the cutting edge would pass through the contact area repeatedly. Increase the rate to 2 or 3 rotations per minute, and the rim travels farther, while the machine still appears slow to an observer. The cutting speed at the rim is therefore not the hardest part of the problem. The harder part is maintaining pressure without forcing the blade out of line. A modern circular saw advances into material through a controlled feed system. The workpiece is held firmly. The blade is supported. The rate of contact is adjusted so that the cutter removes material without binding. For the proposed ancient machine, the granite block might have been placed on a sled or platform. Ropes, wedges, and wooden guides could move it slowly toward the cutter. Workers could add abrasive slurry while others monitored the alignment. The block might instead remain fixed while the entire saw frame moved. That would require an even larger supporting structure capable of sliding or pivoting under load. A third possibility combines both movements. The wheel turns in one plane while the granite rotates or shifts beneath it. This can produce more complicated curvature, but it demands more control. Dunn's model requires the cutter to be tilted at approximately 45 degrees in order to explain the 2 different measured radii. Holding a wheel 11 meters across at that angle would place uneven loads on the bearings and frame. Gravity would pull the outer edge downward, while contact with the stone pushed it sideways. The supporting structure would need strong braces. Large foundation points would be necessary to prevent the frame from leaning. The centre of mass would no longer sit directly beneath the axle in a convenient vertical arrangement. One solution would be to place part of the machine inside a trench. Dunn has suggested that large trenches traditionally identified as boat pits could have provided mounting spaces for such equipment. In his reconstruction, a wheel could stand partly below ground, allowing the axle and support structure to remain at a workable height. A trench certainly helps with scale. Without one, the centre of an 11-metre wheel would stand more than 5 metres above the ground. Workers would need scaffolding simply to reach the axle. Lowering part of the wheel into a pit brings the centre down. The surrounding rock can support the frame, and the cutting area can be positioned near ground level. The difficulty is that a suitably shaped trench is not automatically a machine foundation. Boat pits are recognised elements of Egyptian royal complexes. At Abu Rawash, the wider monument is attributed to Djedefre through excavated inscribed statue fragments, and its archaeological context has been studied over many campaigns. To reinterpret a boat pit as a saw mounting, investigators would need evidence connected to machinery. They might expect axle supports, bearing wear, anchor holes, repeated abrasion from ropes, deposits of stone slurry, copper residues, or unfinished blocks arranged around the work in position. The dimension should also match the proposed wheel. The pit would need to allow the cutter to rotate at the required angle without striking the walls. There should be room for workers, supports, abrasive supply, and movement of the stone. No complete group of such features has been documented around the curved block. The trench idea remains a proposed solution to the mounting problem, rather than evidence that settles it. There is another design that avoids some of these difficulties. Perhaps the 11-metre circle was not a full wheel at all. A long curved arm could carry a smaller cutting head through the same radius. Attach a beam to a pivot, place an abrasive tool at the far end and swing it across the granite. The tool follows part of a circle even though no complete circular blade exists. The same principle can be seen in a compass. A small pencil draws a large circle because it is held at the end of a long arm. The pencil does not need to be the size of the circle. A pivoted stoneworking machine could use a copper shoe, grinding stone, or short blade attached to the end of a beam. Workers would pull the arm back and forth while weights maintained pressure. Moving the pivot or changing the angle could produce overlapping curved surfaces. Such a device would be easier to build than a full 11-metre disc. Its main structure could be timber. The moving cutting element would be small and replaceable. The pivot would still require control, but the total rotating mass would be far lower. Would it produce the Abu Rawash striations? Possibly, although their direction should follow the sweep of the arm. If the lines run in a way that does not match that motion, the model would fail. A pivoted arm might also create a simple cylindrical curve more easily than the compound geometry reported on the block. Creating two large radii would require a change in the arm's orientation, a second pivot, movement of the block, or a more complex linkage. This is possible, but each addition moves us farther from the simple explanation of one tilted disc. A pendulum saw offers another alternative. A long blade suspended from above can swing through an arc. Abrasive beneath the blade removes material from the lowest portion of each swing. The resulting cut has a curved bottom determined by the suspension length. The machine could be large without requiring a huge circular blade. Workers might pull the pendulum from side to side while weights press it downward. The block could be shifted gradually to create a broader surface. Again, the surface geometry becomes the test. A pendulum should leave marks oriented along its swing. A rotating disc should leave marks related to rotation and feed. A rocking straight saw should leave another pattern. The stone should allow us to eliminate some of these possibilities, but only after the marks have been mapped with enough precision. The 11-metre saw hypothesis is therefore best understood as one geometric solution among several. It is not simply a wild idea. A tilted circle can produce the measured radii described by Dunn, and his model demonstrates that relationship. The calculation does not prove that the ancient machine was a full metal disc. It does not identify the blade material, the drive system, or the support structure. It does not show that no smaller tool following a controlled path could produce the same result. There is also a danger in allowing the most dramatic version of the machine to dominate the debate. Once people hear 11-metre saw, they imagine either a lost industrial civilization or an obviously impossible fantasy. Both reactions can prevent a more useful investigation. The ancient device, if there was one, may have looked nothing like a modern saw. It might have been a slow wooden frame carrying copper and abrasive. It might have moved through only a small arc. It might have used ropes and counterweights rather than continuous rotation. Calling it a circular saw could be technically correct while giving the wrong mental picture. The opposite danger is reducing the machine to such a flexible idea that it can explain any mark. If the disc is too difficult, it becomes a pivoted arm. If the arm cannot produce the compound curve, the block is moved. If the striations do not match, a second finishing process is added. At some point, a reconstruction must become specific enough to fail. A serious model should provide dimensions for the frame, axle, supports, cutting rim, and workpiece platform. It should estimate the mass of the moving parts and the force needed to turn them. It should show how abrasive reaches the cut and how waste is removed. The machine should be built at least at partial scale. It should cut granite. The resulting surface should be measured against Abu Rawash. If the model uses a segmented rim, it should predict repeating marks. If it uses loose abrasive, it should predict a certain surface texture. If the cutter is tilted, the measured radii should match its angle and diameter. The experiment should also show how the machine begins and ends a cut. The curved termination on the Abu Rawash block may be more informative than the main hollow, because it could preserve the moment when the cutting edge left the stone. A rotating disc entering the block should create one type of boundary. A pendulum should create another. A grinding arm should leave overlapping arcs. A flexible straight saw might produce a less regular ending. Testing these details would give the theory real value, even if the giant wheel fails. A failed reconstruction could reveal that a different ancient machine is needed. There is no reason to assume that every lost tool must have been more advanced than the tools known today. Some historical technologies disappeared because they were specialized, expensive, or replaced by easier methods. A large wooden stone saw might be ingenious and effective while still being inferior to modern equipment. Its disappearance would not be mysterious. The frame would decay. The copper would be recycled. The workers who understood its alignment would die. Later builders might prefer smaller tools that were easier to maintain. A machine can be forgotten without an entire civilization being erased. The larger builder culture theory makes a different claim. It argues that the scale and precision of the marks exceed what dynastic Egyptian workshops could achieve, so the machinery must belong to an earlier and more technologically capable people. The 11-meter cutter becomes important to that argument because it seems too large, too controlled, and too unfamiliar to fit the standard picture of Old Kingdom stoneworking. If such equipment existed before Djedefre, the curved block might be older than the pyramid complex in which it now appears. That possibility cannot be dated from the curve alone. A radius has no historical period. The same geometry could be produced in the 4th dynasty, an earlier period, or a later quarrying operation if the required tool existed. To connect the mark with a builder culture, investigators need comparable traces in monuments with different histories. They need to show that the same cutting signature appears repeatedly, especially in structures believed to belong to Egypt's earliest monumental phases. This is why the argument moves beyond Abu Rawash. One unusual block can inspire a machine. A repeated pattern across Giza, Abu Sir, Karnak and other sites might begin to suggest a technological tradition. The comparisons must be exact. A curved groove at one site and a straight saw cut at another do not automatically belong to the same equipment. The granite composition, line spacing, arc radius, surface sequence, and archaeological context all have to be considered. If the same coordinated striations appear on several stones, the same process may have been used. If similar abandoned arcs occur at different monuments, a rotating or pivoting cutter becomes easier to defend. If the marks differ under close examination, they may represent ordinary variety within stoneworking rather than one lost machine. The 11-meter saw remains a provocative reconstruction because it turns an irregular block into a precise mechanical proposal. Its scale forces us to ask about materials, bearings, power and workshops, rather than speaking vaguely about advanced technology. But the block cannot tell us whether the proposed machine was common, experimental, ancient, later, or never present at all. For that we must leave Abu Rawash temporarily and follow the marks to other Egyptian sites, where saw cuts, drill grooves, unfinished surfaces, and apparent machining errors have been waiting in plain sight. At Giza, some of those marks were documented long before anyone described them as evidence of a lost builder culture. During his survey of the plateau in the early 1880s, Flinders Petrie examined granite coffers, basalt paving stones, drill holes, stone cores, and discarded fragments. He was interested in the dimensions of the monuments, but he also paid close attention to manufacturing mistakes. A completed and polished surface could hide the earlier work. A saw that ran too deep or a drill that wandered preserved the movement of the tool more clearly. Inside the Great Pyramid, the granite coffer provided one of his most direct examples. Petrie noted places where a saw had entered too deeply and was then backed out. The mark showed that the workers did not simply pound the box into shape and polish the result. Long cuts had been made with a blade operating against the granite. Based on the length of the coffer and the direction of the cuts, he concluded that some straight saws must have been at least 8 feet long. An 8-foot saw is not an 11-metre circular cutter, but it is already a substantial tool. A thin strip of copper that long would bend unless it was supported or tensioned. Workers would probably have needed a frame, controlled pressure, and a way to keep the cutting path supplied with abrasive. Even within the conventional explanation, the operation begins to look less like 2 people casually dragging a loose blade, and more like an organised piece of equipment. The overcuts in the coffer are useful because they record an error. If the saw had stopped exactly where intended, the later finishing process might have removed nearly all evidence of its path. Instead, the blade continued into an area that was supposed to remain intact. The mistake preserved part of the cutting sequence. Petrie also studied fragments from the basalt pavement east of the Great Pyramid. He described one piece with a saw cut that had gone off the course and been abandoned. Another showed regular lines inside the cut. A third had been sawn from both sides and was nearly divided. These pieces demonstrate that large quantities of hard stone were shaped through sawing operations at Giza, although the exact construction of the saws remained uncertain. Basalt is different from granite, but it is not a forgiving material. It is dense, hard, and capable of wearing tools quickly. The surviving pavement fragments suggest a production process in which blocks were reduced to slabs before their exposed surfaces were dressed and polished. A rough saw face was not the final product. It was one stage in a longer sequence. This point matters when comparing Giza with Abu Rawash. The curved granite surface may also preserve an intermediate operation rather than the intended finished form. Petrie's most controversial Giza evidence came from a small piece of diorite and from tubular drill cores. The diorite fragment carried a series of parallel grooves shaped as circular arcs. Petrie believed the only practical explanation was a circular saw. He also examined a granite core with what appeared to be a regular spiral groove running around it for several turns. The groove crossed quartz and feldspar, and Petrie thought its depth remained too consistent to have been made by loose abrasive. He proposed fixed cutting points made from a material harder than quartz. The observations were real. The explanation was an inference. No circular blade was recovered beside the diorite. No tube drill with fixed jewel teeth was found attached to the granite core. Petrie looked at the marks, compared them with the tool technology known to him, and reconstructed a mechanism. That is essentially the same method used in the Abu Rawash argument. The stone is treated as a record of motion. Regular arcs suggest rotation. A spiral suggests that a drill turned while descending. Grooves that remain deep across different minerals suggest a hard and controlled cutting point. The difficulty is deciding whether the marks record one cutting pass, many passes, or a later operation that followed the first. A groove circling a drill core may look like one continuous spiral, even if separate abrasive grains created its visible sections during repeated rotations. The deepest surviving scratch may connect with another scratch by chance, or by following a weakness left in the stone. Later experimental work has shown that copper tools used with abrasive can saw and drill rose granite. It has also shown that the work is demanding, with slow cutting and heavy tool wear. Those experiments weakened the claim that copper-based tools were physically incapable of producing any of the Giza cuts. They did not prove that every line Petrie recorded came from loose sand. The important comparison is not between advanced machines and no machines. The Egyptians were using mechanical systems in either case. A tubular drill turned by a bow, frame, rope, or weighted shaft is a machine. A long saw held under tension is a machine. The disagreement concerns the cutting edge, the degree of control, the speed of material removal, and the size of the supporting equipment. At Giza, there is enough variety to warn us against searching for one universal tool. Straight saw cuts, tubular holes, pounding marks, grinding scratches, polished surfaces, and abandoned mistakes do not all come from the same device. Even two cuts in granite may have been made differently depending on their purpose. A sarcophagus wall requires a long controlled cut. A pivot hole requires a short circular drill. A statue begins with heavy material removal and ends with fine surface work. A basalt paving slab may be sawn roughly and then ground flat. Grouping all these marks under the word machining can hide the fact that several technologies were probably involved. The machine argument becomes stronger only when the same specific signature repeats. That would mean more than finding lines on two stones. The lines should have similar spacing, depth, cross-section and movement. Their relationship to the surrounding surface should match. The same kind of error should appear at the end of the cut. This is why Giza remains central. Petrie recorded several distinct examples in a known monumental setting. The Great Pyramid coffer is not a loose block found kilometers away. It belongs inside the pyramid. The basalt pavement fragments came from a major element of the associated complex. Their presence shows that hard stone sawing was part of Old Kingdom construction at Giza. It does not show whether the workers used ordinary loose abrasive temporarily embedded grains, permanently fixed teeth, or a combination that changed according to the task. A short distance south of Giza, the pyramid field of Abu Sir adds a different set of examples. Abu Sir became a major royal cemetery during the 5th dynasty. Its complexes used limestone for most structural work, but hard stones appeared in important locations. The pyramid temple of Sahur included a basalt-paved court supported by red granite columns, monumental granite doorways, granite wall elements, and hard stone sarcophagi were also used in the royal complexes. Neferefre's burial chamber contained fragments of a red granite sarcophagus, while Sahur's chamber may have held one made from basalt. This matters because Abu Sir shows that the hard stone tradition continued after the largest pyramids at Giza. The scale of the monuments changed, but the ability to transport, shape, fit and finish granite and basalt did not suddenly disappear. Advocates of lost machining point to cut faces and grooves on broken hard stone pieces around the site. Some are described as saw kerfs with regular lines. Others contain curved depressions, narrow channels, or surfaces that appear flatter than expected from pounding alone. The challenge is that many Abu Sir monuments were heavily damaged. Stone robbers dismantled structures over long periods. Sarcophagi were broken, and some fragments were marked for reuse. At one small pyramid, a surviving red granite sarcophagus fragment carried a crossed circle marking indicating that it had been considered for conversion into millstones. The same monument was quarried and disturbed in several later periods. A cut on such a fragment may belong to the original 5th dynasty manufacture, a later attempt to split the sarcophagus, preparation for reuse, or modern excavation damage. Its location beside an Old Kingdom pyramid does not automatically date the mark. This makes Abu Sir useful for another reason. It reminds us that ancient Egyptian stone was often worked more than once. A granite block could begin as part of a royal doorway, be removed centuries later, cut into a smaller object, and eventually be abandoned. Each stage might leave its own grooves. A researcher who assumes all marks are original could combine several periods into one imagined machine. A researcher who assumes every unusual groove is later could dismiss genuine Old Kingdom evidence. The only safe approach is to determine how the marks relate to the object's original form, inscriptions, breaks, and later modifications. Suppose a saw line crosses an original polished face. That cut is later than the polishing. If an inscription ends cleanly at a broken edge while the saw groove runs along the break, the groove may belong to dismantling or reuse. If the cut lies beneath an original finished surface or forms part of the object's intended internal shape, it is more likely to belong to the first manufacturing process. These relationships can sometimes date a tool mark, even when the tool itself is missing. The hard stone elements at Abu Sir also provide a useful test of technological continuity. If Giza's most impressive marks came from a lost builder culture that disappeared before the 5th dynasty, then later Abusia work should show a decline or a different manufacturing signature. Perhaps the later builders reused older granite. Perhaps they copied forms they could no longer produce cleanly. Perhaps the finest pieces were inherited from earlier monuments. That is the proposed pattern, but it has to be demonstrated. The presence of granite in a 5th dynasty temple is not evidence that it was reused. Some pieces may have been newly quarried and shaped. Others may indeed have come from older structures. Each object requires its own history. A comparison should ask whether the Abusia striations match the Giza examples quantitatively. Are their groove intervals the same? Do their saw kerfs have comparable widths? Do the marks cross quartz crystals in the same manner? Are the surfaces produced by similar stages? Without those measurements saying that both sites contain saw marks, tells us only that sawing was used at both sites. That is already accepted. It does not identify an unknown machine. Farther south, Karnak presents an even more complicated situation. Unlike a pyramid complex built mainly during one reign, Karnak developed through repeated construction, demolition, restoration, and reuse over roughly 2,000 years. Kings added pylons, courts, shrines, obelisks, statues, gateways, and walls. Later rulers altered or dismantled earlier work. Loose granite blocks at the site can therefore belong to different centuries. The Franco-Egyptian Centre for the Study of the Temples of Karnak has documented groups of granite blocks from monumental gateways, including around 200 loose pieces associated with the gate of the 7th pylon of Thutmose III. Karnak also contains clear examples of rebuilding. One gateway preserved decoration from Amenhotep III on hidden faces, visible decoration from Rameses III, and reused blocks from Akhenaten inside its masonry. It had been restored, dismantled, and reconstructed before reaching its present form. That history should make us cautious when a groove on a Karnak block is assigned to a single period. A stone may have been shaped for one building, recut for another, and modified again during restoration. Machine advocates have drawn attention to narrow channels, curved recesses, apparent saw lines, and drill holes on hard stone pieces at Karnak. Some marks are described as similar to those at Giza or Abu Rawash because they are regular and cross-hard mineral surfaces. Yet Karnak's most famous granite work also demonstrates processes that do not require an unknown prehistoric culture. New kingdom builders erected large granite obelisks, statues, columns, and doorways. Many carry royal names and decoration integrated into their final design. The objects belong to known building campaigns, even when every manufacturing detail remains uncertain. If a large granite gateway was produced for Thutmose III, it shows that dynastic Egyptian stoneworking remained capable long after the Old Kingdom. It does not tell us whether the same tools were used at Giza. Technology can change while producing similar results. Bronze became more common. Workshop organisation changed. Different abrasives may have been available. Knowledge could improve in some areas and decline in others. A straight groove made in the 4th dynasty and a similar groove made 1,000 years later are not necessarily evidence of one continuous hidden machine tradition. Karnak also helps expose a common problem with visual comparisons. A photograph may show a curved cut on granite without showing the full object. The viewer cannot tell whether it is an original manufacturing mark, a socket for a hinge, a later attachment point, a damaged inscription, or preparation for reuse. The cut looks strange because its purpose has been removed from the frame. A circular depression may once have held a column base or pivot. A narrow channel may have secured a metal fitting. Repeated lines may come from sawing, but the sawing could have occurred when the block was reduced for a later building. The correct question is not simply, could a machine make this? Nearly every deliberate cut in stone involves some form of machine or guided tool. The useful question is, what was this feature for and when was it added? From Karnak, the comparison can move to Aswan, where much of Egypt's granite was quarried. The unfinished obelisk there preserves a very different kind of evidence. Broad hollows around the stone are associated with repeated pounding using hard stone tools. Dolerite pounders have been found in quarry contexts, and the surfaces show the results of heavy impact rather than clean sawing. Hard stone pounders remained important tools for shaping granite, while grinding stones and abrasives were used during later finishing. The Aswan evidence is sometimes treated as proof that all Egyptian granite was shaped by pounding. It does not show that. Quarry extraction and detailed workshop cutting are different tasks. Pounding is effective for removing large amounts of material from an open surface. It is less suitable for producing a narrow straight kerf or hollowing the inside of a box. The surviving quarry marks tell us how workers separated and rough-shaped some large pieces. They do not exclude saws and drills elsewhere in the production sequence. The same object might pass through several methods. Pounders remove the outer mass, saws define deep planes, drills create internal holes, smaller stones and abrasive smooth the surface. Polishing produces the final finish. Looking for one tool to explain the entire object is like trying to build a house with nothing but a door handle. The handle is useful, but it arrives rather late in the proceedings. At Saqqara, the large hard stone boxes associated with the Serapeum are often added to the discussion. Their internal corners, flat surfaces and massive lids appear difficult to produce. Alternative researchers point to straightness, polish, and occasional tool marks as evidence of advanced equipment. These boxes belong mainly to much later periods than the 4th Dynasty pyramids. Their existence proves that Egyptian workshops continue to handle very large granite objects. They cannot be used as direct evidence that one prehistoric group created every hard stone monument. They may preserve related methods, improved methods, or techniques developed independently. The boxes should be measured in the same way as the Abu Rawash block, with attention to unfinished areas rather than only the polished faces. Memphis has supplied additional sawn fragments. Petrie described a piece of hard stone cut on several faces, probably waste from roughing out a statue. Such fragments are valuable because they show production rather than display. A finished statue may hide the tool path, waste preserves it. When the examples from all these sites are placed together, a broad pattern becomes clear. Ancient Egyptian craftspeople sawed, drilled, ground, pounded and polished hard stone. They used large tools as well as small ones. They made errors. They abandoned cuts. They reused old material. None of that is controversial. The unresolved question is whether a narrower pattern appears inside the broad one. Do certain stones preserve marks that cannot be recreated by known abrasive tools? Do compound curves, coordinated striations and regular arcs recur often enough to identify a specialized machine? Answering this requires more than a collection of dramatic photographs. Each mark needs a record of location, object type, stone composition, orientation, dimensions, archaeological date, and later history. The surfaces should be scanned using the same equipment. Groove spacing should be measured by the same method. Investigators should avoid selecting only the most regular lines. The rough, broken, and weathered areas matter because they show how much alteration the object has experienced. A database could then group marks by physical characteristics rather than by site reputation. Perhaps one family of grooves appears on Old Kingdom granite coffers, another appears on later reused blocks, a third belongs mainly to basalt paving. The results might reveal a common machine. They might instead show several ordinary tools leaving superficially similar traces. A particularly strong signature would include 3 kinds of agreement. First, the large-scale geometry would match, such as the same radius or relationship between curved surfaces. Second, the microscopic grooves would match in shape, spacing, and mineral damage. Third, the archaeological sequence would place the marks in the same broad period. If all 3 agree across Abu Rawash, Giza and Abu Sir, the case for a shared Old Kingdom process becomes much stronger. If the same signature also appears at Karnak on clearly New Kingdom work, that may indicate long technological continuity rather than a vanished pre-dynastic culture. If it appears only on reused stones whose first context is uncertain, The older builder proposal gains room but still lacks a date. There is another possibility. The marks may identify a lost dynastic machine that was never shown clearly in Egyptian art. Tomb scenes do not provide a complete catalogue of workshop equipment. Perishable frames, ropes, and wooden supports may have vanished. The surviving depictions may simplify complicated processes or focus on socially meaningful stages. A machine could be known to a small group of royal specialists and used only for expensive hard stonework. Its components might be dismantled and recycled when a project ended. Later generations could lose the technique without any earlier civilization being required. This explanation would account for sophisticated marks, missing equipment, and a clear dynastic context. It is less dramatic than a lost builder culture, but it is not a minor possibility. Recovering an unknown Old Kingdom mechanical system would still change our understanding of ancient engineering. The broader comparisons do not yet prove one explanation. They show that the Abu Rawash block is not alone in raising technical questions. Giza contains documented saw errors, regular grooves, and drilled cores. Abusir contains extensive hard stonework and a complicated history of destruction and reuse. Karnak contains granite from many building periods, often moved and recut. Aswan preserves quarrying stages that remind us how varied the process was. The similarities are enough to justify a coordinated study. They are not enough to declare that every remarkable mark came from one machine or one unknown people. To reach that larger conclusion, the argument must move beyond tools and surfaces. It must identify the builders themselves. It must explain when they lived, where they worked, what other objects they produced, and why their equipment vanished while their stonework remained. That is where the proposal changes from a mechanical hypothesis into a historical one, because the claimed builder culture is not simply a better equipped team of Egyptian craftspeople. It is presented as an earlier society whose monuments were already standing when dynastic kings arrived to use them. It is presented as an earlier society whose monuments were already standing when dynastic kings began attaching their names to them. In the strongest version of the idea, this builder culture possessed advanced knowledge of geometry, stone cutting, transport, and large-scale construction. Its people shaped granite with machines that later Egyptians inherited but could not fully reproduce. Pharaohs repaired the old sites, added inscriptions, replaced damaged sections, and adapted the structures to their own religious system. There are several versions of this theory, and they should not be treated as one fixed claim. Some supporters place the builders only a few centuries before the First Dynasty. Others place them thousands of years earlier, before major climatic changes transformed northern Africa. Some imagine a local Egyptian culture that developed advanced methods and then collapsed. Others suggest influence from an unknown civilization outside Egypt. The more extreme versions often add lost energy systems, global navigation, or knowledge inherited from survivors of a catastrophe. Those additions are not required by the basic argument. The simplest builder culture proposal says only that some major Egyptian stonework may be older than the kings normally associated with it. That is already a major historical claim. The argument usually begins with the apparent difference between early monumental stonework and what came before it. Pre-dynastic Egyptians built settlements, tombs, ceremonial structures, and mud brick architecture. Then, during the 3rd and 4th dynasties, enormous stone complexes appeared. Within a relatively short period, builders moved from large mastabas and royal enclosures to Djoser's step pyramid, Sneferu's pyramids, the Great Pyramid, and the other monuments of Giza. To some observers, this development looks too rapid. The Great Pyramid is not a small experimental structure with uncertain angles and walls that lean in several directions. It is an enormous, carefully planned monument containing millions of blocks, precisely aligned sides, internal chambers, passages, relieving spaces, and carefully fitted hard stone elements. If this was the result of a developing tradition, supporters of the older builder idea ask where the earlier stone buildings are. Where are the smaller granite workshops? Where are the crude practice pyramids? Where are the generations of abandoned machines that should come before the finest work? The standard archaeological answer is that development is visible, but it does not appear in the neat form people sometimes expect. Pre-dynastic Egypt did not consist of a few isolated farmers who suddenly woke up one morning and decided to build pyramids. Between roughly 4000 and 3000 BCE, communities along the Nile developed more specialized crafts, long-distance trade, organized production, social hierarchy, administrative practices, and increasingly powerful regional centers. By the later Naqada period, writing was emerging, elite burials had become much richer, and political authority was becoming more concentrated. The surviving architecture from this period was mostly made from mud brick, wood, reeds, and other materials that do not survive as well as stone. Funerary architecture changed gradually from simple pits to rectangular tombs, some lined with mud brick. Large ceremonial and administrative structures also appeared, although the archaeological record does not show a widespread tradition of enormous stone construction before the dynastic period. This is important because missing buildings do not always mean missing people. A society can be organized, technically skilled, and politically ambitious, while building mainly with materials that decay. Mud brick walls collapse, timber roofs disappear, reed structures leave little more than post holes and stains in the soil. Stone survives and therefore dominates our impression of the past. We see the pyramid more clearly than the towns, sheds, storage buildings, temporary ramps, wooden frames, rope systems, and workers' shelters that supported its construction. The builder culture hypothesis interprets this survival problem in a different way. It suggests that the missing early stone tradition may not be missing because it never existed. Its monuments may have been claimed by later rulers, while its tools, settlements, and records disappeared. That possibility cannot be rejected simply by saying that archaeologists have not found the culture. Archaeology is full of societies that were recognized only after the right settlement, burial ground, or workshop was discovered. Many ancient Egyptian settlements remain buried beneath later cities, river sediment, cultivated land, or modern development. The Nile Valley is especially difficult. People repeatedly occupied the same useful areas near water and farmland. Later houses were built over earlier houses. Flood deposits covered settlements. Farmers reused mud brick as fertilizer. Stone was taken from old structures and placed in new ones. A lost settlement is therefore possible. A lost civilization capable of constructing several of the largest monuments on Earth presents a larger problem. A culture that quarried, transported, and shaped millions of tons of stone would require more than a few talented individuals. It would need workers, food, storage, administration, transport routes, specialized crafts, and places where tools were made and repaired. If large machines were used, there should have been frames, bearings, ropes, metal components, abrasives, replacement parts, and waste from failed pieces. Even when most of the equipment was perishable, the production system should leave repeated patterns. An 11-meter cutting machine would not spend its evenings folded neatly inside a small cupboard. It would require a substantial working area. The expected evidence would include unfinished stones carrying the same cutting sequence, foundation points for equipment, deposits of granite slurry, specialized abrasives, copper residues, broken cutting elements, transport installations, and settlements capable of supporting the workforce. The absence of one part can be explained. Wood decays, copper is recycled, rope disappears. The absence of nearly every connected part becomes harder to explain when the technology is said to have been common across several major sites. This does not mean that no unknown machines existed. It means that the scale of the proposed culture should match the scale of the evidence required. Abu Rawash gives us a useful test because it contains genuine remains from before Djedefre. Cemetery M includes 25 mud brick tombs dating to the middle of the First Dynasty. These were substantial elite burials, and their discovery helped clarify the development of early pharaonic society. Radiocarbon work on material from First Dynasty tombs at Abu Rawash has also helped place the reign of King Den and the early development of the Egyptian state within a measured chronological framework. The results connect the cemetery with the known early dynastic sequence, rather than with an unknown civilization from a much earlier age. These discoveries prove that Abu Rawash was important before the 4th dynasty. They show that elites used the site centuries before Djedefre built his pyramid complex. They do not show evidence of giant stone saws. The tombs are made largely from mud brick. Their architecture belongs to the developing Egyptian funerary tradition, seen at other early dynastic sites. The pottery, burial practices, administrative objects, and tomb designs connect them with the culture that became dynastic Egypt. There is no clear break in which one technically advanced population disappears and an unrelated, less capable population replaces it. Instead, the record shows continuity mixed with rapid change. Continuity does not mean that every technology survived. A craft can disappear within the same civilization. A royal workshop might develop a specialized process, use it for several reigns, and then lose it after political or economic disruption. Knowledge can also become restricted. If only a small group understood how to align a particular machine or prepare a particular abrasive, the method might vanish when the group was dispersed. This would create lost Egyptian technology without requiring a pre-Egyptian builder culture. The development of monumental architecture also becomes less sudden when the sequence is examined closely. Pre-dynastic and early dynastic rulers built increasingly large tombs and enclosures. Mud brick remained important, but plans became more complex, labour became more organised, and royal building acquired greater symbolic and administrative importance. Djoser's complex at Saqqara marked a major expansion in stone construction. Its buildings often copied forms originally made from wood, reeds, and mud brick. Stone columns resembled bundled plants. Stone doors imitated open wooden doors. Solid ceremonial buildings reproduced structures that had once been made from lighter materials. The complex looks less like a completely foreign technology dropped into Egypt and more like Egyptian architecture being translated into stone. The builders were doing new things with a durable material while preserving older forms they already understood. Djoser's complex is generally regarded as the earliest preserved large stone architectural complex in Egypt, and the step pyramid stands at the beginning of the surviving pyramid tradition. The next stages were not perfectly smooth. Sneferu's pyramid projects show changes in design, angle, and construction method. The bent pyramid altered its slope partway up. The pyramid at Meidum experienced major structural failure or collapse at some point in its history. The red pyramid used a shallower angle and became the earliest successful large true pyramid. These buildings look like a program of experimentation. Lessons from one project appear to affect the next. Engineers adjusted the slope, internal arrangement, masonry, and construction planning. That pattern is difficult to reconcile with the idea that 4th dynasty rulers merely inherited a collection of completed monuments from a technically superior culture. It does not make inheritance impossible, but it gives the dynastic builders an active role in developing pyramid architecture. The Great Pyramid also belongs to a larger archaeological setting. It is surrounded by cemeteries connected with Khufu's family and officials. Quarries, roads, temples, work areas, settlement remains, administrative seals, animal bones, pottery, and other material connect construction activity with the 4th dynasty state. The evidence is not a complete instruction manual. Archaeologists still debate ramps, lifting systems, workforce organisation, and the final stages of construction. But the Giza plateau does not look like an abandoned prehistoric monument that received only a few later inscriptions. It looks like an active royal construction landscape. One of the strongest pieces of direct evidence comes from Wadi el-Jarf on the Red Sea coast. Excavations there uncovered papyri dating to the end of Khufu's reign. The documents belong to teams working for the royal administration. The journal of an official named Mera records the movement of limestone from the Tura quarries to the Great Pyramid project at Giza. Other records describe supplies, tools, and the activities of organised work groups. They do not explain how every block was lifted, and they say nothing about the Abu Rawash granite surface. They do show that Khufu's government was actively transporting building stone to his pyramid while it was under construction. This creates a serious problem for the strongest inheritance claim. If the Great Pyramid had been completed thousands of years before Khufu, why was a team under Khufu transporting fine limestone to the site described by the pyramid's name? A supporter of inheritance could answer that Khufu was restoring or casing an older structure. That is possible in principle. Fine Tura limestone may have been used for exterior casing, temples or related buildings rather than the core. The papyri do not stand beside Mera and announce, "Today we constructed the pyramid from the first course upward." They do, however, place organised 4th dynasty construction at the monument. The more evidence that must be reinterpreted as restoration, the more complicated the inheritance model becomes. The same issue appears with construction marks. Quarry and mason marks have been found on blocks within Giza monuments, including locations that were sealed during construction. Such marks can include crew names and royal references. They are different from a visible inscription carved onto an exposed wall centuries later. A mark hidden between blocks or inside a construction space is difficult to explain, as a pharaoh simply adding his name to an old monument. This does not mean every royal name proves original construction. Egyptian rulers certainly reused monuments. They erased earlier names, inserted their own inscriptions, moved statues, rebuilt temples, and took blocks from older structures. A cartouche on an exposed surface can show ownership, restoration, dedication, or later control. Context decides how much the inscription tells us. The builder culture argument is strongest when it points to uninscribed stonework that appears technically different from later additions. A massive granite block may contain fine cutting marks, but no royal name. A surrounding wall may be rougher and carry later inscriptions. Supporters interpret the contrast as evidence of two construction periods. The original builders produced the precise megalithic core. Dynastic rulers added smaller masonry and decoration. Sometimes that interpretation may be correct. Egyptian sites often contain several phases. A temple can have an Old Kingdom foundation, a Middle Kingdom repair, a New Kingdom gateway, and a Roman wall. Different quality does not automatically mean different civilization. A royal granite chamber and an outer mud brick wall can belong to the same building project, while serving different purposes. An experienced hard stone team may produce work unlike that of ordinary masons. A finished ceremonial surface may be precise, while hidden packing stones remain rough. Budget, function, location, deadline, and available labour all affect workmanship. Even modern buildings contain polished stone in the entrance and concrete blocks behind the service cupboard. The age of the stone cannot settle the question. Granite may be hundreds of millions of years old geologically, but the tool marks are much younger. The cut itself contains no organic material that can be radiocarbon dated. Investigators date worked stone through its context. Mortar, charcoal, rope, wood, plant fibres, and other materials trapped during construction can be sampled. The relationship between the sample and the building must then be examined carefully. Old wood creates a known difficulty. A beam may be reused for decades before becoming part of a monument. Charcoal can come from an old tree. Contamination can alter a result. Even with those limits, large radiocarbon programs have dated hundreds of organic samples from Old and Middle Kingdom monuments. The results broadly support construction within the historical Pyramid Age, although individual samples can be older than expected and require contextual interpretation. Newer projects improve this by selecting material from clearly documented locations and combining laboratory results with archaeological sequences. Work on 5th Dynasty monuments at South Saqqara, for example, has dated rope, textiles and charcoal from specific construction or burial contexts, and used those results to refine the chronology of King Djedefre. A pre-dynastic builder culture should produce a different pattern. Organic material sealed beneath original foundations or inside primary construction joints should repeatedly date centuries or millennia earlier than the associated royal period. One old sample would not be enough. Reused wood and natural contamination can create isolated anomalies. A consistent group of early dates from several secure positions would be much harder to dismiss. The same standard applies to weathering. Some arguments for older monuments rely on erosion that appears too heavy for the accepted date. The Great Sphinx is the most famous example, with claims that parts of its enclosure show damage caused by heavy rainfall. Weathering can be difficult to interpret because stone does not erode at one fixed rate. Different layers of limestone respond differently. Groundwater, salt, wind, rainfall, repairs, sand cover, and exposure all affect the surface. A deeply weathered wall may be older than a nearby smooth wall, or it may simply be made from weaker stone. Dating erosion requires geological mapping and a clear history of exposure. The builder culture theory often combines weathering, machining marks, and architectural precision. Each line of evidence is uncertain by itself, but supporters argue that the pattern becomes persuasive when the clues are placed together. The oldest major sites appear to contain some of the largest stones. Hard granite contains unusual grooves. Certain monuments show heavy erosion. Later structures are sometimes smaller or less precise. Pharaohs are known to have reused older work. This cumulative argument deserves more than a casual dismissal. It identifies real features that require explanation. Its weakness is that the features do not all point to the same date or the same people. A saw mark shows a manufacturing process. It does not date the process. Erosion suggests exposure. It does not identify the builder. Reuse proves that later Egyptians inherited some earlier structures. It does not prove that they inherited all early monuments from a separate civilization. A persuasive historical theory must connect those clues through evidence that belongs together. What would that evidence look like? A granite object with advanced marks would need to be found in an undisturbed pre-dynastic layer. The layer should contain datable organic material. Similar pieces should appear at more than one site. Waste and unfinished objects should show the same manufacturing sequence. A workshop might preserve abrasive deposits, tool supports, broken machine components, or repeated mounting points. A settlement should contain the food, pottery, burials, and administrative evidence of the people who operated it. Their material culture should be distinguishable from that of known Nakada or early dynastic communities. Perhaps they used different pottery, burial customs, measuring systems, or construction standards. Without that cultural layer, the builder society remains defined mainly by the monuments attributed to it. The reasoning becomes circular. The stonework is too advanced for known Egyptians, so unknown builders must have made it. We know the unknown builders were advanced because the stonework attributed to them is advanced. To escape that circle, the theory needs an independent sign of the builders. The absence of writing cannot be used as strong evidence either way. A technically capable society might leave few texts, particularly if it used perishable writing materials. Yet large construction projects usually create administration. Workers must receive food, tools must be counted, transport must be scheduled, quarry teams must know which blocks are required, someone has to decide who receives the final loaf of bread, a responsibility that has probably caused administrative tension since the invention of lunch. Egypt's developing writing system was closely connected with ownership, taxation, offering, storage, and state control. The appearance of writing alongside political unification is exactly what we might expect from a society beginning to manage larger projects. An older builder culture may have used another system. If so, traces of that system should appear on tools, containers, quarry walls, transport labels, or building blocks. The lack of such evidence does not make the culture impossible, it keeps it hypothetical. There is also a simpler explanation for the impression that Egyptian stoneworking began at its peak. The surviving monuments are not a random sample. Royal projects received the best labour, the most valuable materials, and the strongest political support. Small experimental objects were more likely to be reused, broken, buried, or overlooked. Large royal monuments survived because they were large, protected, and difficult to remove completely. Our first clear view of a technology may therefore come from an advanced royal project rather than from its earliest trial. The missing practice pieces might be sitting inside later buildings, beneath settlements, or in quarry debris that has not been recognised. Egyptian development could also accelerate quickly once the state was unified. A central government could gather specialists from different regions, support them with agricultural surplus, and maintain projects for years. A stoneworker who was previously limited to small vessels could join hundreds of others in a royal workshop. Knowledge that had existed on a small scale could be expanded through organisation. The sudden change may be less about the invention of every technique and more about the concentration of labour and resources. None of this explains the Abu Rawash block in detail. The curved surface still requires a toolpath. The fine striations still need microscopic study. The proposed compound cut still needs replication. The dynastic context tells us who was active at the site. It does not tell us what every machine looked like. A lost mechanical system remains possible within dynastic Egypt. A deeper pre-dynastic origin remains possible only if new evidence connects the stoneworking to that earlier period. The difference is important. We do not know the tool does not mean we do not know the culture. Archaeologists can identify the society that built a monument while remaining uncertain about parts of its engineering. We know who built medieval cathedrals, but historians still debate how some loads were lifted and how particular workshop methods were organised. Missing technical details do not automatically transfer the building to another civilization. At the same time, royal attribution should not become untouchable. Every block should be studied on its own evidence. A monument can contain older material. A king can restore an earlier site. A statue can be recarved. A sarcophagus can be moved. Djedefre's inscribed statue fragments connect him firmly with Abu Rawash, but they do not place his name on the curved granite block. His builders may have shaped it. They may have reused it. Later stone robbers may have cut it. The surviving context does not yet settle that sequence. The builder culture proposal therefore survives in a narrow space between what is possible and what has been demonstrated. It is possible that Egyptian rulers inherited older sacred locations and incorporated existing structures. We know they did this in many periods. It is possible that some tools were lost and some machines were built mainly from perishable materials. It is possible that a block at a disturbed site has a history older than the monument beside it. What has not been established is a technologically advanced, pre-dynastic population responsible for the main megalithic monuments of Egypt. The current archaeological record shows gradual social development from pre-dynastic communities into the early state, monumental mud brick construction in the first and second dynasties, major stone innovation under Giza, experimentation under Sneferu, and enormous state projects during the fourth dynasty. It also provides administrative settlement, quarry and dating evidence that connects pyramid construction with dynastic Egyptian rulers. That sequence may be incomplete. It may hide forgotten machines and misunderstood workshop methods. It may even contain older structures that were absorbed into later complexes. To decide how far inheritance really went, we have to examine what Egyptian rulers did when they encountered monuments from the past. We need to look at restoration, recutting, reinscription, reuse, and the specific evidence connecting Djedefre with Abu Rawash, because a monument can belong to a king in more than one way. A monument can belong to a king because he ordered it, because he completed it, because he repaired it, because he moved it, or simply because he placed his name on it. Ancient Egypt provides examples of all these possibilities, which is why royal inscriptions must be read in context rather than treated as ownership labels that answer every question. Later pharaohs sometimes reused the work of earlier rulers. Statues were moved to new locations, faces were altered, inscriptions were replaced, and old building blocks were placed inside new walls. A colossal statue originally made for Amenhotep III was moved and reinscribed by Meneptah roughly a century and a half later. The original king's features remained visible even though another ruler's names were cut deeply into the statue. Later, kings also reused Middle Kingdom monuments, both to save labour and to connect themselves with respected rulers of the past. This was not a secret practice. Egyptian rulers did not always pretend that they had quarried every block personally, which would have been difficult to believe even with a very confident royal inscription. Reusing a monument could be practical, political, religious, or all three. A statue made from valuable granite might be carried to another temple rather than abandoned. A doorway could be dismantled and rebuilt somewhere else. A ruler might restore an old sanctuary to show respect for the gods. Another might erase a predecessor's name because the predecessor had become politically inconvenient. The evidence for reuse is usually visible because the later work does not fit the original design perfectly. A new inscription may cut across older decoration. A face may have been reshaped while the body keeps the style of an earlier period. A stone may carry decoration on a hidden side because it was turned around and placed inside a later wall. Archaeologists can often reconstruct these stages by studying the direction of carving, the style of the figures, the names of rulers, the position of the block, and the surfaces concealed during rebuilding. This established history gives the builder culture theory a reasonable starting point. Pharaohs did inherit monuments, they did alter old structures, they did move and claim objects created by previous rulers. The important question is how far that practice can be extended. There is a large difference between saying that Djedefre reused an older granite block and saying that he inherited an entire pyramid complex from a technologically advanced civilization. The first possibility requires evidence concerning one object. The second requires the architectural, archaeological and historical evidence for the whole site to be reinterpreted. At Abu Rawash, the attribution to Djedefre does not depend on one cartouche scratched onto an exposed wall. Excavations on the eastern side of the pyramid uncovered fragments of quartzite royal statues, some bearing inscriptions. These finds allowed the monument to be connected with Djedefre, the son of Khufu, and a ruler of the 4th dynasty. Later investigation identified the expected elements of a royal funerary complex and an associated elite cemetery. The nearby cemetery F also contains 4th dynasty mastabas linked with Djedefre's reign. Archaeologists identified connections through the architecture, pottery, masonry, and burials of at least 2 royal sons associated with the king. This is not the kind of evidence expected from a ruler who merely visited an abandoned structure, placed a statue near it, and left before lunch. It shows that Djedefre's court was actively developing a royal funerary landscape at Abu Rawash. The site also contains remains from before Djedefre. Cemetery M includes 25 mud brick tombs dating to the middle of the 1st dynasty. The tombs contained pottery, stone vessels, ivory objects, copper pieces, and other material connected with early dynastic elite society. Their presence proves that Abu Rawash was important, centuries before the 4th dynasty pyramid complex was built. This earlier use may have influenced Djedefre's choice of location. He could have selected a landscape already associated with status, ancestry, or ritual importance. Royal builders often worked in places whose history was part of their value. The 1st dynasty cemetery does not demonstrate that a pyramid or advanced granite workshop existed there before Djedefre. Its surviving architecture belongs to the known early dynastic tradition of large mud brick tombs. No giant cutting machine, megalithic stone complex or industrial granite workshop has been securely identified within those earlier levels. That does not prove the curved granite block was made during Djedefre's reign. It means that the known earlier occupation does not currently provide the missing builder culture required by the larger theory. The block remains difficult because it is not securely fixed in its original architectural position. It is a damaged object at a heavily quarried site. Its present location cannot tell us exactly when it was cut, what it was intended to become, or whether every mark belongs to the same working period. It may have been shaped for Djedefre's complex. It may have been a failed object abandoned during construction. It may have been reused from an earlier monument. It may have been cut again when later workers dismantled the pyramid for stone. Several of these events could have occurred in sequence. Suppose the block began as part of a granite sarcophagus or architectural fitting. 4th Dynasty workers may have cut its main surface. The piece could then have cracked and been rejected. Centuries later, quarry workers may have tried to divide it for reuse, leaving an additional arc or step. The final surface would preserve evidence from 2 different technologies. Looking at it today, we might attempt to explain every feature with one machine even though no single machine made them all. The opposite sequence is also possible. An older stone could have been brought to Djedefre's complex and modified to fit a new purpose. The original curve might belong to an earlier workshop, while the rougher marks belong to dynastic alteration. To demonstrate that sequence, investigators would need to show which marks cross or interrupt the others. They would need to identify changes in weathering, polishing, mineral damage, and surface deposits. A mark cut into an already weathered surface is later than the weathering. A polished line softened by later abrasion is older than the abrasion. This is ordinary archaeological reasoning, but the small scale of the features makes the work difficult. Thousands of years of exposure can blur the difference between one stage and another. Royal inscriptions face the same sequencing problem. A name carved into a finished monument may be original or later. A construction mark hidden inside masonry carries a different kind of weight, because it was never intended for public display. The most secure attribution comes from several forms of evidence agreeing with one another. Inscriptions, architecture, associated burials, pottery, construction sequence, administrative records, and dating evidence should point toward the same period. At Giza, that combination is much stronger than the popular claim that Khufu's name appears only in a suspicious location. The Wadi el-Jarf papyri came from the end of Khufu's reign and belonged to a working team connected with his administration. The Journal of Mera records the transportation of fine limestone from the Tura quarries to the Great Pyramid project at Giza. The archive also includes accounts and records of organised teams, supplies, and royal work. The documents do not describe every construction technique. Mera does not explain how granite was drilled, how the upper courses were lifted, or how a curved block at Abu Rawash was made. He does provide direct evidence that Khufu's administration was transporting stone to the Great Pyramid while the royal project was active. The material was probably connected with the fine outer casing and related structures. Pierre Tallet describes Mera as an eyewitness to the construction project, not as a tourist making notes about an ancient ruin. An inheritance theory can still be adjusted around this evidence. It can propose that Khufu added casing to an older core, restored an earlier pyramid, or built temples around an existing monument. Any one of those possibilities is physically imaginable. The problem is that each new piece of dynastic construction evidence requires another adjustment. The limestone becomes restoration material. The workers' settlement becomes housing for repair crews. Construction marks become later additions. Royal cemeteries become developments around an inherited sacred object. The more evidence that has to be reassigned, the more complicated the theory becomes. A complicated theory can be true, but it needs direct evidence for the complication. There should be a visible boundary between the original structure and the later work. Construction methods should change at that boundary. Dating samples should separate into 2 clear periods. The older section should contain features inconsistent with the later building campaign. Without that division, the simpler explanation remains that the 4th Dynasty state built the monument while using techniques that are not yet completely understood. Abu Rawash is less securely preserved than Giza, which leaves more room for uncertainty. Djedefre's complex was extensively quarried, and much of its stone was removed. loose fragments cannot always be returned to their original positions. The construction sequence is therefore harder to reconstruct. Even so, the excavated evidence connects the royal complex and its associated cemetery with Djedefre's reign. An older builder theory would have to explain why a 4th dynasty royal program fits so closely around the supposedly inherited monument. Perhaps Djedefre found an older pyramid and chose it as his funerary site. He then added temples, statues, burials, and new masonry. That would not be unprecedented in principle. Egyptian rulers restored older sacred places, yet a reused monument usually preserves evidence of the earlier phase. Different masonry styles, buried inscriptions, older foundations, altered alignments, or structural joints reveal that later builders were working around something already present. The older phase at Abu Rawash has not been established in this way. The curved block cannot provide the entire missing phase. It is one object with an uncertain original position and a disputed manufacturing process. This does not make it irrelevant. A single object can sometimes overturn an accepted history. It must first be understood securely enough that other explanations fail. The necessary investigation begins with documentation rather than argument. The block should be scanned in 3 dimensions at very high resolution. The large concavity should be tested against cylindrical, elliptical, and irregular surface models. The proposed radii should be recalculated from thousands of points rather than a few hand measurements. The curved ending should be mapped independently. Investigators could test whether it shares the geometric relationship predicted by one tilted circular cutter. Every visible striation should be recorded. Software could measure spacing, depth, direction, and side-to-side movement. If several lines wander together, the degree of coordination could be calculated rather than judged by eye. Microscopic analysis could examine how the grooves cross quartz, feldspar, and mica. A fixed hard cutting point may fracture those minerals differently from loose abrasive. A rotating cutter may leave a directional pattern unlike a reciprocating saw. Residues should also be studied. Traces of copper, abrasive minerals, later contamination, or conservation materials might remain in protected depressions. Finding copper would not identify the exact machine, but it would support the involvement of a copper-based tool. Finding a deliberately selected abrasive harder than common quartz sand could reveal a more effective ancient cutting system. The experiments would then need to reproduce the whole surface. One team might use a long, straight copper saw in a weighted wooden frame. Another might test a rocking or pendulum saw. A third might use a pivoted grinding arm. A fourth could build a scaled version of the tilted circular cutter proposed by Dunn. All groups should use comparable granite and record their procedures in detail. The finished surfaces should be scanned and compared blindly with the ancient block. The test should not be decided by which replica looks most impressive in a photograph. The comparison should use measurable criteria established in advance. Does the tool create the same radii? Does it leave the same line spacing? Do the grooves have the same cross-section? Does the cutting process produce the observed steps naturally, or must those be added afterward? A successful copper and abrasive replication would not prove that every Egyptian hardstone object was made in the same way. It would show that an available dynastic method can explain Abu Rawash without requiring a vanished industrial system. A successful rotating machine replication would show that Dunn's geometry is mechanically realistic. It would still not date the machine or identify the builders. The historical question would remain. To support a pre-dynastic builder culture, similar marks would need to be found in secure context older than dynastic Egypt. A loose block at a disturbed pyramid site is not enough. The ideal discovery would be an unfinished granite object inside a sealed early workshop, accompanied by datable material, manufacturing waste, and remains of the tool support system. One securely dated workshop would be more valuable than hundreds of internet photographs. The dating material would need to relate directly to the work. Charcoal from a nearby campfire might belong to an unrelated visitor. Wood reused in a machine could be older than the machine. Sediment could move through cracks. Archaeologists would therefore look for several samples from controlled positions. If ropes, wooden supports, food remains and workshop deposits all pointed to the same unexpectedly early period, the builder culture theory would gain serious support. Tools would not need to survive completely. A stone bearing, an axle socket, a row of anchor holes, unusual copper fragments, or repeated abrasive deposits could reveal the design. The production waste should match the finished monuments. Granite chips, sawn offcuts, drill cores, broken blades, and rejected pieces should preserve the same marks seen at Giza and Abu Rawash. A culture capable of monumental construction should also leave evidence of its people. Their settlements, burials, pottery, diet, trade, and administration may be modest compared with their stonework, but they should not be entirely absent. Until such evidence appears, the pre-dynastic builder culture remains a proposed explanation for difficult objects, rather than an archaeologically identified society. The conventional account also remains incomplete. It can connect Djedefre with Abu Rawash and Khufu with Giza. It can demonstrate that copper and abrasive are capable of cutting granite. It can point to dynastic quarries, work crews, administrative records, and developing pyramid architecture. It has not reconstructed every hard stone operation. It has not built a full working system that explains every claimed feed line, compound curve, deep drill groove, and abandoned arc. That gap should not be hidden behind the phrase copper and sand. The materials may be correct while the machine that controlled them remains unknown. Egyptian builders may have used frames, guides, counterweights, pivoting arms, tension systems, and carefully prepared abrasives that are poorly represented in surviving images. Such equipment could be sophisticated without belonging to an earlier civilization. A wooden workshop machine would vanish much more easily than a granite block. Copper fittings would be recycled. Ropes and leather would decay. The knowledge could disappear when royal funding ended, or specialist crews were dispersed. This may be the most reasonable form of lost technology in the Egyptian record. Not electricity, not steel factories, and not a secret machine capable of melting stone, but carefully designed mechanical equipment made from ordinary ancient materials. It would still be a remarkable discovery. The mystery therefore survives, but in a more limited and useful form. We do not have strong evidence that an unknown civilization constructed Egypt's major pyramids before the pharaohs. We do have hard stone surfaces whose exact manufacturing sequences remain debated. We know that Egyptian rulers reused earlier monuments. We do not know that Djedefre inherited the Abu Rawash pyramid from a separate builder culture. We know that copper and abrasive can cut granite. We do not yet know whether the tested systems fully reproduce the curved Abu Rawash block. We can calculate an 11-metre circle from the proposed geometry. We cannot turn that calculation into a recovered 11-metre saw. This may sound less dramatic than choosing one side and declaring the matter solved, but it gives the stone more respect. The block should not be used as a stage prop for a conclusion chosen before the measurements begin. It deserves to be scanned, tested, compared, and placed into a reliable sequence. Perhaps the results will show that a long straight saw bent under pressure while workers rocked it through abrasive. Perhaps they will reveal a pivoted frame that no one has yet reconstructed properly. Perhaps the compound curves will fit a large rotating cutter so precisely that the machinery question becomes impossible to avoid. Any of those results would teach us something important about ancient Egypt. The possibility that usually receives the least attention may be the most interesting. The tool could turn out to be neither primitive nor impossibly advanced. It may occupy the large middle ground where most real technology lives. A machine made from timber, copper, rope, stone bearings, weights, and selected abrasive could look simple after it was understood. Before it was reconstructed, its marks might look impossible. Ancient craftspeople did not divide their equipment into the categories we use today. They were not trying to be conventional or alternative. They were trying to finish the stone without breaking it, exhausting the workforce, or explaining to the royal supervisor why the sarcophagus now had an unexpected opening in the side. Their solutions came from repeated practice. A workshop learned which sand cut fastest, how tightly to tension a blade, how much weight a frame could take, and when a strange sound meant that everyone should stop pulling. Those practical details rarely entered royal inscriptions. A pharaoh recorded victories, offerings, divine ancestry, and the dedication of monuments. He did not usually record the recommended abrasive grain size for a granite saw. The missing instructions invite speculation because the finished work remains while the daily knowledge has vanished. That may be why the curved block at Abu Rawash continues to attract attention. It is not a famous statue or a complete royal monument, it is a manufacturing trace. It seems to preserve the movement of a tool without preserving the tool itself. The broad hollow tells us that material was removed along a controlled curve. The smaller arc suggests that the position changed. The steps may record separate operations. The striations preserve repeated contact between a tool, abrasive, and granite. What they do not tell us directly is who held the tool, how fast it moved, what supported it, or which century witnessed the work. Those answers must come from careful comparison rather than confidence. So did ancient Egypt use machines we no longer understand? Almost certainly, in the ordinary sense that some workshop equipment and specialized procedures have been lost. The surviving archaeological record cannot show every wooden frame, guide, lifting rig and abrasive system used across 3,000 years of Egyptian history. Did those machines include an 11-meter circular saw at Abu Rawash? The current evidence does not establish that. The proposed saw is a geometric reconstruction that needs better measurements and practical testing. Did a technologically sophisticated culture build Egypt's oldest monuments before dynastic Egypt and leave them for the pharaohs to claim? That remains unsupported by a secure archaeological culture, workshop, tool system, or consistent early dating pattern. Egyptian reuse makes inheritance possible in individual cases, but it does not by itself transfer the major pyramid complexes to unknown builders. The answer may be less satisfying than a clean yes or no, but the uncertainty is not empty. It points towards specific work that can be done. The block can be scanned, replicas can be cut, microscopic marks can be compared, other sites can be recorded under the same standards. Context can be studied without assuming that every unusual surface is original or later. A good mystery becomes clearer when it produces better experiments. And now, after following a damaged piece of granite from a ruined pyramid site through saws, abrasives, lost workshops, royal reuse, and the possibility of an earlier culture, we return to the object itself. It remains where it began, a curved surface carrying fine lines surrounded by broken stone. The block has not given us a lost civilization, it has given us a question about ancient skill. That question may be more valuable because it does not require us to underestimate the Egyptians or invent an answer for them. It allows their technology to be clever, incomplete in our records, and still open to investigation. Wherever you are listening from tonight, consider the oldest worked stone you have ever seen. How much of its making could you reconstruct from the marks alone? How many tools would have disappeared? How many movements would remain hidden beneath the polished surface? If this quiet investigation has helped you look at ancient Egypt with a little more curiosity and a little less certainty, you can like the video, subscribe, and share it with someone who enjoys a mystery that does not need to shout. For now, the granite keeps its final details. It tells us that a tool moved across it, that someone controlled that movement, and that the work was more complicated than a single phrase can explain. The machine may have been familiar to the builders. It is unfamiliar to us. That difference is where the mystery remains.